Hello everyone and welcome. In this video, we're diving into Git trunk-based development. This is a modern approach to collaborative software development. Let's explore how this strategy can transform the way your team works together. So, what exactly is trunk-based development? At its core, it's a source control branching model where developers collaborate on code in a single branch. This single branch is often called trunk or main. This method avoids long-lived feature branches. The key idea here is that developers commit small frequent changes directly to the main branch. Alternatively, they might use short-lived feature branches. These short-lived feature branches are quickly merged back into the main branch. This approach promotes continuous integration and faster feedback loops. Now let's explore the core principles that make trunk-based development work so well. First, we have small frequent commits. Developers commit code in small manageable chunks. These smaller chunks are easier to review. Also, they are less likely to cause conflicts. Secondly, short-lived branches are crucial. Feature branches should only exist for a short period, ideally just hours or days, not weeks. These branches are merged quickly to prevent them from drifting too far from the main trunk. Continuous integration is another key principle. All changes are automatically built and tested before merging. This ensures that the trunk remains stable and always deployable. Finally, feature toggles are used. Incomplete features are hidden behind toggles. This allows code to be merged into the trunk, while keeping unfinished features invisible to users until they are fully ready. Now let's compare trunk-based development with Git Flow. Git Flow is another popular branching strategy. In trunk-based development, we primarily work with a single main branch, often called trunk or main. Feature branches are short-lived, typically lasting only hours or days. The focus is on continuous integration with smaller and more frequent commits. In contrast, Git Flow uses multiple long-lived branches, such as main, develop, and feature, release, and hotfix branches. This results in more complex merge patterns and larger, less frequent merges. Git Flow is often used in projects with scheduled releases, while trunk-based development is favored for continuous delivery environments. Let's take a look at how to implement trunk-based development in your daily workflow. First, start your day by pulling the latest changes from the trunk or main branch. This ensures you're working with the most up-to-date code. Next, create a short-lived feature branch for your specific task. Make small focus changes in this branch. Before pushing your changes, run tests locally to catch any issues early. Then create a pull request for code review. This allows your team to review your changes and provide feedback. Finally, after the continuous integration process passes and your code is approved, merge your feature branch back into the trunk. Here are some common Git commands you'll use daily. To start, check out the main branch and pull the latest changes. Create a short-lived feature branch. Make your changes and commit them with a descriptive message. Finally, push your branch to the remote repository and create a pull request for review. Let's explore feature toggles and their role in trunk-based development. Feature toggles, also known as feature flags, allow developers to merge incomplete features into the trunk. These features remain hidden from users until they are fully ready for release. Feature toggles enable continuous integration of work in progress. It separates deployment from feature release. Also, it allows for A/B testing and gradual rollouts, and reduces merge conflicts and integration issues. However, feature toggles require careful management to prevent technical debt. Here's a simple example of how to implement feature toggles in your code. Define a feature flags object with Boolean values for each feature. Create a function called showFeature that checks the status of a feature flag. In your application code, use the showFeature function to determine whether to display a feature or not. Now, let's delve into the importance of continuous integration in trunk-based development. The continuous integration workflow starts when a developer pushes code to a short-lived branch. The continuous integration server automatically builds the application. Then it runs automated tests, including unit, integration, and end-to-end tests. Code quality checks such as linting, static analysis, and code coverage analysis are performed. After the code passes all checks and is approved, it is merged into the trunk. Continuous integration helps catch integration issues early and maintains trunk stability. Here's an example of a GitHub Actions workflow file. This workflow is triggered on pushes to the main and feature branches. It sets up the Node.js environment, installs dependencies, runs linting, and executes tests. Let's explore some benefits of using continuous integration in trunk-based development. It catches the integration issues early and maintains the trunk stability. Let's recap the benefits and challenges of trunk-based development. The benefits are faster integration and feedback cycles, reduced merge conflicts and integration debt, improved team collaboration and visibility, simplified release management, and better code quality through continuous testing. However, trunk-based development also presents some challenges. It requires strong testing practices and discipline. Feature toggle management can become complex. It often necessitates a cultural shift for teams used to long-lived branches. There can be a learning curve for breaking down large features, and it demands a robust continuous integration and continuous delivery infrastructure. In conclusion, trunk-based development is a powerful approach that enables teams to deliver high-quality software faster. However, it requires investment in testing, automation, and team practices. Thank you for watching. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Hello and welcome. This presentation will explore how to leverage Git in modern continuous integration and continuous delivery pipelines. We will explore how Git helps in automating the software development lifecycle. Git, a distributed version control system, lies at the heart of many automation workflows. We will also discuss continuous integration and continuous delivery, along with automation to better understand Git's role. Let's begin by understanding the fundamentals of continuous integration and continuous delivery, and then discuss Git's role. Continuous integration is the practice of merging code changes from multiple developers frequently, ideally, multiple times a day. Continuous delivery builds on top of continuous integration by automating the software release process. Continuous deployment takes it a step further by automatically deploying every change to production. By adopting these practices, you can reduce integration problems and improve the software quality. Git serves as the single source of truth for all code changes in a continuous integration and continuous delivery pipeline. Git commits and merges can trigger continuous integration and continuous delivery pipelines, initiating automated builds, tests, and deployments. Git also provides robust versioning and traceability, which are essential for managing changes and rolling back if needed. As an example, a simple git push command to a feature branch can trigger a continuous integration and continuous delivery pipeline, automatically building and testing the changes. Let's walk through a typical Git-based continuous integration and continuous delivery workflow. The first step is to develop new features or fix bugs in a dedicated feature branch. Next, the changes are committed and pushed to a remote repository. This push event triggers the continuous integration pipeline, where automated tests and builds are executed. After the tests pass and the code is reviewed via a pull request, the feature branch is merged into the main branch. Finally, the continuous delivery pipeline automatically deploys the changes to production or other environments. Here are some common Git commands used in this workflow. The git checkout b feature/login page command creates a new feature branch for developing a login page. The git commit m add login functionality command commits the changes with a descriptive message. The git push origin feature/login page command pushes the feature branch to the remote repository, triggering the continuous integration pipeline. Git offers several essential features that are crucial for continuous integration and continuous delivery pipelines. Git tagging allows you to mark specific points in the repository's history, which is useful for release management and versioning. Branching strategies such as Git flow and trunk-based development help manage code changes and collaborate effectively. Protected branches enforce code quality by requiring reviews and checks before merging. Pull or merge requests facilitate code reviews and discussions before integrating changes. Webhooks enable real-time notifications and trigger pipelines automatically on specific Git events. Here are some examples. The Git tag of version 1.2.3m, release version 1.2.3, command creates a semantic version tag. The git push origin v1.2.3 command pushes the tag to the remote repository. The git tag list command lists all the available tags. Additionally, webhooks can be configured in GitHub or GitLab repository settings by providing a URL, selecting relevant events like push and pull requests, and setting the content type to application or JSON. This allows the Git repository to automatically trigger continuous integration and continuous delivery pipelines on relevant events. Choosing the right branching strategy is essential for efficient continuous integration and continuous delivery. Here's a typical branching diagram that explains the different branching workflows. Let's discuss two popular branching strategies. Git flow uses multiple long-lived branches, such as main and develop, along with feature, release, and hotfix branches. This approach is well suited for scheduled release cycles, but can result in complex merge processes. Trunk-based development, on the other hand, relies on a single main branch or trunk and short-lived feature branches. This strategy is ideal for continuous deployment, enabling faster integration cycles and quicker releases. Choose a strategy that aligns with your team's workflow and release goals. Let's explore how Git hooks can enhance continuous integration and continuous delivery pipelines. Git hooks are scripts that run automatically on specific Git events, such as commits, pushes, and merges. These scripts are located in the .git/hooks directory of your repository. Git hooks can be classified as client-side and server-side hooks, depending on whether they run on the developer's local machine or on the remote server. Git hooks enable you to automate quality checks and enforce coding standards before code even reaches your continuous integration system. For instance, a pre-commit hook can run linters and unit tests to ensure that only high-quality code is committed. Here's an example of a pre-commit hook. This script first echoes a message, then runs linters using npm run lint and tests using npm test. If any of these commands fail, the commit is aborted to prevent bad code from being committed. Continuous integration configuration can be stored directly in your Git repository, enabling version control of your pipeline definitions. Here's an example of a GitHub Actions workflow defined in a YAML file. This workflow is triggered on push events to the main and develop branches, as well as on pull requests to the main branch. The workflow defines a build job that runs on Ubuntu, checks out the code, and performs other continuous integration steps. Here's an example of a GitLab continuous integration and continuous delivery pipeline defined in a YAML file. This pipeline defines stages such as build, test, and deploy. The build stage installs dependencies and builds the application, and is triggered only on the main branch and merge requests. The GitLab continuous integration and continuous delivery pipeline supports branch-specific configurations, which enables you to define different pipelines for different branches. Pipeline history is tracked alongside the code in Git, providing full traceability and auditing capabilities. To optimize your Git workflow for continuous integration and continuous delivery, consider these best practices. Always protect your main branch by requiring code reviews and passing continuous integration checks before merging. Implement semantic versioning using Git tags with the major.minor.patch format for clear release tracking. Follow a structured commit message format like conventional commits to automate versioning and changelog generation. Keep your repository clean by using .gitignore to exclude build artifacts, dependencies, and environment-specific files. Use shallow clones in continuous integration pipelines with git clone Depth equals 1 to speed up the checkout process. Finally, use Git Large File Storage, also known as Git LFS, for storing large files outside the main repository to keep Git operations fast. For complex projects, Git submodules and monorepos can be valuable. Git submodules allow you to manage projects with multiple repositories as a single unit. Monorepo tools help manage large codebases within a single repository. Some popular tools for managing monorepos are Lerna and NX. Git Sparse Checkout lets you check out only specific directories to speed up continuous integration. This is particularly useful for microservices architectures, where you may only need to build and test specific services. Sparse Checkout can be initialized using Git Sparse Checkout init, cone, and directories can be specified using Git Sparse Checkout set frontend/src config. Conditional continuous integration, based on changed paths, allows you to trigger specific continuous integration jobs only when relevant files have been modified. This can be achieved by checking if specific files have changed using git diff and grep commands. In summary, Git is the foundation of modern continuous integration and continuous delivery pipelines, enabling automation, version control, and collaboration. Choosing the right branching strategy and leveraging Git hooks can further improve your workflow. Storing continuous integration and continuous delivery configurations in Git ensures traceability and reproducibility. Here are some resources to help you continue your Git continuous integration and continuous delivery journey. Read the Pro Git book by Scott Chacon for a comprehensive understanding of Git. Refer to the GitHub Actions and GitLab continuous integration and continuous delivery documentation for detailed information on configuring continuous integration and continuous delivery pipelines. Finally, check out the Atlassian Git tutorials for practical guidance on using Git effectively. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Let's explore the best practices for managing binary assets within your Git repositories. We will cover the common issues and effective strategies for handling these files. This includes how to keep your repository efficient and maintainable. We will also discuss the tools and techniques you can employ. First, let's define binary files. These are files that aren't plain text, such as images with extensions like PNG, JPG, and GIF, videos like MP4 and MOV, audio files like MP3 and WAV, PDFs, documents, and compiled executables. Unlike text files, binary files present unique challenges when using Git. They are not easily diffable, meaning you can't see the changes between versions as clearly as with text files. They also lead to inefficient storage because Git stores full copies of each version, resulting in repository bloat over time. This can significantly slow down clone and fetch operations and make merge conflicts very complex. Here are a couple of commands that help you to examine the binary files in your repository. To list all the binary files, you can use the command git ls files, no empty directory pipe zargs file pipe grep, ibinary. This command lists all files, pipes that list to the file command which determines the type of file, and then we grep, grep, for the string binary. This will give you a list of all binary files in your repository. To check the overall repository size, use git count objects vh. This provides a human-readable output of the space used by your Git objects. To find the largest files in your Git history, use git revlist, objects, all pipe grep f then open parenthesis git verify git/objects/pack/asterisk .idx pipe sort, kvian pipetail-10 pipe, awk then single quote print $1 single quote close parenthesis. This command helps identify which large files are contributing most to your repository size. The .gitignore file is crucial for excluding unnecessary files from your repository. It is important to ignore generated binary files, build artifacts, and dependencies, ensuring that only relevant source code and assets are tracked. Use file extension patterns to match the files you want to exclude, like star.png or start.mp4. You can also consider creating a global .gitignore file to exclude IDE-specific files across all your projects. Remember to document any exceptions with comments, explaining why certain files are not being ignored. For example, you could include the following in your .gitignore file. Under the comment images, add *.png, *.jpg, *.jpeg, *.gif. Under the comment videos and audio, add *.mp4, *.mov, *.mp3, *.wave. To include certain files, you can add them under the comment exceptions. For instance, !assets/logo.png ensures that this specific PNG file is always included, even if all other PNG files are ignored. Git Large File Storage, or LFS, is an extension that helps manage large files more effectively. To set it up, first install Git LFS using the command git lfs install. Then track specific file types with git lfs track, followed by the file pattern, such as *.psd or *.zip. This tells Git LFS to manage these file types. Finally, add the .git attributes file to your repository using git add.git attributes. Git LFS works by replacing large files with text pointers in Git, while storing the actual file contents on a remote server. This prevents your repository from becoming bloated with large binary files. To check which patterns are being tracked, use git lfs track. To list all LFS files in your repository, use git lfs ls files. If you need to download the LFS content, use git lfs pull. The .git attributes file allows you to define specific attributes for files in your repository. It is used to mark files as binary to prevent merge conflicts, define custom diff and merge strategies, and set line-ending behavior for specific files. You can also configure Git LFS tracking patterns within this file. Additionally, it's possible to apply filters for specific file types, enabling custom processing. In the sample.git attributes file, you can mark files as binary, which means Git won't try to create a diff for them. We can add *.png binary, *.jpg binary, *.pdf binary. To track files with LFS, you can add *.psd filter equals lfs diff equals lfs merge equals lfs text, and *zip filter equals lfs diff equals lfs merge equals lfs text. You can also define custom diff tools for specific formats, such as *.docsdiff equals word. If you've already committed binary files to your repository, you might want to remove them to reduce its size. To remove a file from all commits, use git filter branch, force, index filter, then single quote gitarm, cached, ignore unmatched path /to/ large file, zip single quote, prune empty, tag name filter cat, all. However, be aware that this rewrites Git history, which can be disruptive. Only use this on private branches or with careful team coordination. As an alternative, the BFG repo cleaner is designed specifically for removing unwanted files, and it's generally faster than filter branch. To remove files larger than 10 megabytes, use javajar bfdjar. Striplobs bigger than 10 repo.git. To remove specific files, use javajar bfdjar. Delete files *, open curly brace zip, PDF, jar close curly brace repo.git. In addition to Git LFS, there are other ways to manage binary files. External storage solutions involve using content delivery networks, or CDNs, for media assets. You can also store binaries in services like S3 buckets, or use artifact repositories for builds. The key is to reference these external resources in your code, rather than including the files directly in the repository. You can implement download scripts in your continuous integration and continuous delivery, or CI/CD, pipeline to fetch these resources when needed. Git submodules and subtrees offer another approach, where you separate binary assets into dedicated repositories and then link them to your main repository using either Git submodules or subtrees. This allows for selective cloning of binary content and independent versioning, helping to keep your main repository smaller. Let's summarize the best practices for managing binary files in Git. Regularly audit your repository for large binary files to identify potential issues early on. Maintain comprehensive .gitignore and .gitAttributes files to ensure that unnecessary files are excluded and proper attributes are set. Utilize Git LFS for managing necessary binary assets, especially when they are large and frequently updated. Consider external storage solutions for very large media files to keep your repository lean. Clean up your Git history to remove old, large binary files before they become problematic. Document your binary file strategy for your team to ensure everyone follows the same guidelines. By following these practices, you can keep your repositories lean, improve performance, and create a better development experience for everyone on your team. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this video, we are going to explore the internal object storage system of Git. We will learn about how Git organizes and stores data. Let's begin our journey into Git internals, focusing on the objects that form the foundation of its version control system. Git operates as a content-addressable file system. All the data is stored as objects inside the .git/objects directory. There are 4 primary types of objects: blobs, trees, commits, and tags. Each object is uniquely identified by its secure hash algorithm 1#, also known as SHA-1#. A blob, which stands for binary large object, stores the actual content of a file. Blobs are content addressable, meaning they are identified by their secure hash algorithm, 1# of their content. Git stores only the file content, not the file name or permissions within the blob. If different commits have identical file content, they will share the same blob object. To create a blob object from content, you can use the command echo hello git pipegit hashobject-w-stin. This command creates a blob and outputs its secure hash algorithm 1#. To view the blob's content, use the command git cat-file-p followed by the secure hash algorithm 1#. The output will be the content, hello git. To check the object type, use the command git cat-file-t followed by the secure hash algorithm 1#. This command will output blob. Blob objects are stored within the .git/objects directory. The first 2 characters of the secure hash algorithm 1# are used as the subdirectory name, and the remaining characters are used as the file name within that subdirectory. For example, the blob with secure hash algorithm 1# AF5626B4A114AP2D6 3DB7-082-RES4756051B would be stored in the file git/objects/AF/5626B4A114AP2D6 3DB7-082-4756051B. The content of the blob is compressed using zlib. The format of a blob is blob followed by a null character, followed by the content length, another null character, and finally the content itself. A tree object represents a directory in Git. Trees store the file modes, which are the permissions, the object types, which can be a blob or another tree, the secure hash algorithm 1 object references, and the file names. Trees create a hierarchical structure, linking to blobs, which represent files, and other trees, which represent subdirectories. To create a tree from the index, first add a file using the command git addfile.txt, then use the command git write-tree. This command outputs the secure hash algorithm 1# of the newly created tree. To view the content of a tree, use the command git cat-file-p followed by the secure hash algorithm 1# of the tree. To check the object type, use the command git cat-file-t followed by the secure hash algorithm 1 hash of the tree, which will output tree. Here's an example of how trees organize a project's file hierarchy. The root tree contains entries for the top-level files and directories. Each subdirectory is represented by another tree object. The files within those directories are represented by blob objects. The root tree's content will point to a blob for a file named readme.md and to another tree representing the source directory. The source tree would then contain blob objects for main.c and utils.c. The file modes indicate the type of file, with 10644 representing a regular file, 10755 representing an executable file, 040,000 representing a directory, and 120,000 representing a symbolic link. A commit object represents a specific version of your project. It stores a reference to a tree which represents the snapshot of the project, the parent commit or commits references, the author information including name, email and date, the committer information, and the commit message. Commits form a directed acyclic graph, or DAG, that represents your project's history. To create a commit, you can manually create a commit object using the command echo tree7b20e547993359ec218dd2a0d0day1a6c49c2c parent 9c689d4b70a0a6 347c9eb31f9c4b6if5f7ecc author John Doe less than John at example.com greater than 163387 2000-0400 committer John Doe less than John at example.com greater than 163387 2000-0400 add readme file pipe git hash object-t commit-w-stin. To view the commit object, you can then use the command git cat-file-p followed by the secure hash algorithm 1 hash. Commits are organized into a directed acyclic graph, showing the history of your project. Each commit points to its parent or parents tracing back to the initial commit. Examining the commit history can be done using the command git log -1 line. This shows a concise log of commits. To visualize the relationships between commits, use the command git log -graph -1 line. This displays a graph of the commit history, illustrating branches and merges. A tag object creates a permanent reference to a specific commit. Tags store the object reference, usually a commit, the object type, usually commit, the tag name, the tagger information including name, email and date, and an optional message. There are 2 types of tags, lightweight and annotated. Lightweight tags are simply a reference to a commit, whereas annotated tags are full tag objects with metadata. To create an annotated tag, use the command git tag-a version 1.0-m, version 1.0 release. This creates a tag named version 1.0. To view the tag object, use the command git cat-file-p followed by version 1.0. To create a lightweight tag, use the command git tag version 1.0-beta. A lightweight tag is just a reference, so using git show on a lightweight tag will simply show the commit it points to. Let's summarize the different Git object types. A blob stores file content without any metadata. Multiple files with identical content share the same blob. To create a blob, use the command git #object-w file.txt. A tree represents directories and file hierarchies, containing pointers to blobs and other trees with metadata. To create a tree, use the command git write-tree. A commit points to a tree snapshot along with author and committer information, timestamp, message, and parent commits. To create a commit, use the command git commit-tree less than tree secure hash algorithm greater than -p less than parent secure hash algorithm greater than. A tag creates a permanent reference to a specific object, usually a commit, with optional metadata. To create a tag, use the command git tag-a less than name greater than less than commit secure hash algorithm greater than. All Git objects are content addressable via secure hash algorithm 1 hashes and are stored in .git/objects. Together they form a complete, Immutable history of your project's file system. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this video, we're diving deep into the inner workings of Git to explore references. We'll uncover how Git cleverly tracks branches, tags, and the special head pointer, all of which are essential for navigating your project's history. Get ready to understand Git at a more fundamental level. So, what exactly are Git references? Simply put, references are pointers to specific commits in your repository's history. These pointers are stored as simple text files within the .git/ref/ directory. They are how Git keeps track of important positions in your project, such as where your branches and tags are pointing. Some common examples of references you might be familiar with are branches, tags, and the head reference. As illustrated in the diagram, the .git directory contains a refs folder, which then organizes references into heads for branches, tags for tags, remotes for remote branches, and the head, which is a special reference. Let's take a closer look at branch references. A branch in Git is essentially a lightweight, movable pointer to a commit. It's stored as a file within the .git/ref/head/ directory. This file contains nothing more than the secure hash algorithm 1 hash of the commit that the branch is currently pointing to. Here are some examples of how these references are used. To view the content of a branch reference, you can use the command cat followed by .git/ref/head/master. The output will be a long string, which is the secure hash algorithm 1 hash of the latest commit on the master branch. When you create a new branch using the git branch command, Git creates a new file in the .git/ref/heads directory with the name of the new branch. The content of this file will be the secure hash algorithm 1 hash of the commit that the new branch was created from. Now let's explore how branches move as you make commits. When you commit changes on a branch, the branch reference automatically moves forward to point to the new commit. Git simply updates the corresponding file in the .git/ref/heads directory with the new commit secure hash algorithm 1 hash. This is what makes branches so lightweight. They're just tiny text files containing a secure hash algorithm 1 hash. The branch you are currently on is determined by the head reference. The diagram here shows a series of commits, C1, C2, C3, and C4. The master branch initially points to C3. After a new commit C4 is added, the master branch automatically moves forward to point to C4. Before the commit, the .git/ref/head/master file contains the secure hash algorithm 1 hash of commit C3. After the commit, it's updated to contain the secure hash algorithm 1 hash of commit C4. Let's discuss the head reference. Head is a special pointer that tells Git which branch you're currently working on. It resides in the .git/head file in your repository. Usually, head contains a symbolic reference to a branch, indicating that you're on that branch. When you switch branches using the git checkout command, Git updates head to point to the branch you checked out. For example, to view the content of head, you can use the command cat followed by .git/head. It typically contains ref:/ref/head/master, indicating that you're currently on the master branch. If you then switch to another branch, such as feature, using the git checkout feature command, the content of the .git/head file will change to ref:/ref/head/feature, reflecting the switch to the feature branch. Now let's explore the concept of a detached head state. This occurs when head points directly to a commit instead of a branch. This typically happens when you check out a specific commit, tag, or remote branch. In this state, the .git/head file contains the direct commit secure hash algorithm 1 hash instead of a symbolic reference to a branch. An important thing to keep in mind is that any commits made in the detached head state will be lost, unless you create a branch to save them. The diagram shows the difference between a normal head state and a detached head state. In a normal state, head points to a branch reference which in turn points to a commit. In a detached head state, Head points directly to a commit without any branch referencing it. Next, we will understand tag references. Tags are references that point to specific points in Git history. Unlike branches, tags are designed to be permanent and don't move when you make new commits. They're stored in the .git/ref/tags directory. There are two types of tags: lightweight tags, which are simple pointers to commits, and annotated tags, which are full Git objects containing metadata like the tagger name, email, and a message. Here are some examples. To create a lightweight tag, use the command git tag followed by the tag name such as v1.0. This creates a new file in the .git/ref/tags directory containing the secure hash algorithm, 1 hash of the tagged commit. To create an annotated tag, use the command git tag -a followed by the tag name, -m, followed by a message. Annotated tags point to tag objects, which can be viewed using the git cat file command. Let's discuss remote references. These references are pointers to the state of branches on remote repositories. They're stored in the .git/ref/remotes directory. These references are updated whenever you use the git fetch or git pull commands to synchronize your local repository with the remote repository. Remote references are read-only, meaning you can't directly modify them. They help Git keep track of what's on the remote server. The diagram here shows a local repository on the left and a remote repository on the right. The local repository has a local branch called master and a remote tracking branch called origin/master. The remote repository has its own master branch. When you fetch or pull from the remote repository, Git updates the origin/master branch in your local repository to reflect the state of the remote master branch. In summary, Git references are simple pointers to commits stored as text files. Branches located in the .git/ref/heads directory are movable pointers that update with new commits. Head, residing in the .git/head file, points to the current branch or commit. Tags stored in the .git/ref/tags directory are permanent pointers to specific commits. Remote references found in the .git/ref/remotes directory track the state of remote branches. Understanding references is crucial for effectively navigating and manipulating Git history. Some useful commands for exploring Git references include git show ref, which shows all references; git symbolic ref head, which shows where head points; git update ref to create or update a reference; and git for each ref for detailed information about all references. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. In this video, we will explore the concept of Git pack files. Pack files play a crucial role in how Git efficiently stores repository data. Let's dive in to understand how they work. Git stores all the content of your repository as objects within the .git/objects directory. Each of these objects is uniquely identified using a SHA-1 hash. There are 4 primary types of objects. First, the blob, which typically represents file content. Second, the tree, which represents directories. Third, the commit, which represents a snapshot of your repository. And fourth, the tag, which is a named reference to a specific point in your history. Initially, these objects are stored as individual files, known as loose objects. Storing each file version as a separate object leads to some problems. It can result in inefficient storage, especially for large repositories. Managing thousands of small files can negatively impact file system performance. And network transfers become slow when dealing with a large number of objects. Pack files provide a solution by combining multiple objects into a single file and storing only the deltas, or differences, between objects. This significantly reduces storage requirements and improves network transfer efficiency. A pack file is Git's solution for efficiently storing and transferring repository data. It is a single file that contains multiple Git objects. Pack files use delta compression to reduce the size of the repository. A pack file consists of two files, one with a .pack extension and another with a .idx extension. These files are typically created during operations like git gc, git push, or git fetch. The .pack file contains the actual compressed objects, while the .idx file serves as an index to help Git quickly locate objects within the pack file. Delta compression is a key technique used in pack files. Instead of storing complete copies of similar files, Git stores the base version and only the differences or deltas between versions. As you can see, there is a base version of the file. Then the delta instructions describe how to transform the base version into the modified version. The delta instructions include operations such as copy and insert. By applying these instructions, Git can reconstruct the modified version from the base version, which saves a significant amount of space. Git provides several commands to work with pack files. The git gc command performs garbage collection and creates pack files. The git repack command is used to repack loose objects into pack files. The git verify pack command validates the contents of a pack file. And git count objects command displays the object count and size of the repository. In the example, you can list pack files in the .git/objects/pack directory. You can also use git verify pack to examine pack file contents. Pack files are created in several situations. This includes automatic garbage collection, which is triggered by the git gc command. Network operations such as git push and git fetch also initiate pack file creation. Cloning a repository using git clone will also create pack files. Lastly, manual repacking using the git repack command will result in pack file creation. Git automatically decides when to create pack files based on repository size and the number of loose objects. The threshold for this can be configured in Git settings. Pack files offer several significant benefits. One of the primary benefits is storage efficiency. They reduce repository size through delta compression. Pack files also improve performance by reducing the number of files, which leads to faster file system operations. Network transfers are accelerated because smaller data size and fewer files make cloning, fetching, and pushing much faster. Git handles pack file creation and maintenance automatically, optimizing repository storage without requiring manual intervention. In conclusion, pack files are a critical component of Git that enable it to efficiently handle repositories of any size. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. Welcome. This video explains Git garbage collection, focusing on optimizing repository performance and size. Git garbage collection is a crucial process for maintaining efficient and healthy Git repositories. Git garbage collection is a process that optimizes your repository by cleaning up unnecessary files and compressing them for better performance. Consider it similar to your operating system's garbage collector reclaiming memory. Git gc reclaims space and improves efficiency, ensuring your repository remains lean and fast. Why should you use Git garbage collection? There are several compelling benefits. Firstly, it offers improved performance by optimizing the internal database structure and reducing the time needed for searching objects. Secondly, it provides reduced storage space by compressing loose objects into pack files, significantly decreasing the overall repository size on disk. Thirdly, it enhances network efficiency as smaller, optimized repositories are faster to clone, push, and pull across networks, especially beneficial for large teams. Lastly, regular garbage collection aids in repository maintenance by removing unreachable objects and optimizing references, thus ensuring a healthy repository. Let's explore some basic Git gc commands. The standard garbage collection is initiated with the command git gc. This runs a basic garbage collection operation, which Git automatically performs periodically during normal operations. For a more thorough optimization, use aggressive garbage collection with the command git gc aggressive. This process takes longer but produces better compression and is recommended for repositories with many objects. Lastly, there is auto garbage collection with the command git gis auto. This command checks if garbage collection is necessary based on internal thresholds and runs only if needed. Now let's discuss advanced git gc options. The prune option allows you to prune all unreachable objects immediately, without waiting for the grace period. Use the command git gis prune equals now. Other values can be time specifications like 2 weeks ago. Custom configuration allows you to customize when automatic garbage collection triggers by setting thresholds for loose objects and pack files. Use the commands git config gc at auto 256 and git config gc at auto pack limit 50. Quiet mode suppresses all output from the garbage collection process. This is useful for scripts or when running gc in the background. Use the command git gc quiet. To force repack aggressively repacks the repository. A flag ensures all objects are included and removes redundant pack files after repacking. Use the command git repack add. Here are some git gc best practices to keep in mind. Timing matters. Run aggressive garbage collection during off hours or low activity periods, as it can temporarily slow down Git operations while running. Schedule GC operations during nights or weekends for large repositories. Regular maintenance. For active repositories, run standard GC weekly and aggressive GC monthly to maintain optimal performance. Automate GC with cron jobs or CI/CD pipelines for consistency. Before major operations, run garbage collection before large pushes, pulls, or migrations to ensure optimal network transfer speeds and reduce storage requirements. Always run GC before archiving or transferring repositories. Monitor repository size. Keep track of your repository size over time. Unexpected growth might indicate the need for more aggressive garbage collection or cleanup. Use git count objects v to check repository statistics. In summary, Git garbage collection optimizes repository performance and reduces storage requirements. Basic commands include git gc aggressive, and git gc auto. Advanced options allow fine-tuning of the garbage collection process, and regular maintenance keeps repositories healthy and efficient. Remember that Git's automatic garbage collection works well for most cases, but manual intervention can significantly improve performance for large or busy repositories. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Let's explore Git Filter Branch. This is a tool used for rewriting repository history at scale. Git Filter Branch is a powerful tool specifically designed for rewriting Git repository history. It rewrites commit history using custom filters and operates on entire branches at once. With Git Filter Branch, you can modify files, commit messages, and even authors. This tool is useful for removing sensitive data. Though it is considered a legacy tool, it is still very powerful. Let's discuss some common use cases for Git Filter Branch. First, removing sensitive data. You can purge passwords, application programming interface keys, or personal information that was accidentally committed to the repository history. Second, repository restructuring, where you can move files or directories to different locations while preserving their history, or extract a subdirectory into its own repository. Third, fixing author information, where you can correct author names and email addresses across the entire commit history to maintain consistent attribution. And fourth, cleaning large files, where you can remove large binary files or datasets that bloat repository size, making cloning and operations faster. The basic command structure for Git Filter Branch is git filter branch, then options, followed by revision list options. A common example is Git filter branch with the environment filter option. In the environment filter option, and if condition checks for a specific email address, and if the condition is true, it exports a new email address. The head option at the end specifies the commits to filter. Now let's discuss some common filter types. First, the environment filter. It modifies commit metadata, such as author and committer information. Second, the tree filter. It modifies files in the working directory for each commit. Third, the index filter. It modifies staged files and it's faster than a tree filter. Fourth, the message filter. It rewrites commit messages. And fifth, the subdirectory filter. It extracts a subdirectory as root. Let's see an example of removing sensitive data using Git filter branch. Here, we use the index filter to remove a file containing sensitive data from all commits. The command is git filter branch force index filter, then git remove cached, ignore unmatch and the file name, then prune empty tag name filter cat and all. After running filter branch, force push to overwrite the remote history and ask collaborators to rebase their work. Let's explore an example of changing author information. We'll use the environment filter to modify author and committer information. The command is git filter branch environment filter. Inside the filter, and if condition checks for the old email address. If it matches, the script exports the new author email and the new author name. You can update both author and committer information in the same command by also checking and modifying git committer email and git committer name. Now let's consider extracting a subdirectory into its own repository while preserving its commit history. The command is git filter branch subdirectory filter the path to the subdirectory, prune empty and all. After running this command, the specified subdirectory becomes the new project root, and all commits that didn't affect this directory are removed. Let's talk about the performance considerations while using Git filter branch. Filter branch can be extremely slow on large repositories. Each commit is checked out and rewritten, which is resource intensive. Memory usage can spike with large files, or many commits in temporary files can consume significant disk space. Git documentation recommends using Git filter repo instead of filter branch for better performance. Now let's discuss some optimization tips. Use index filter instead of tree filter when possible. Limit the range of commits with revision options. Use prune empty to remove commits that become empty, and run on a fresh clone with no local option. For very large repositories, consider using Git filter repo, which is up to 100 times faster than filter branch. Here are some best practices to keep in mind. Always create a backup of your repository before running filter branch. This operation rewrites history and cannot be easily undone. Inform all collaborators before rewriting history. They will need to rebase their work or reclone the repository after your changes. Run filter branch operations on a fresh clone first to verify the results before applying to your main repository. After running filter branch, carefully inspect the new history to ensure the desired changes were made correctly before pushing. Let's discuss some modern alternatives to Git filter branch. First, Git filter repo. This is a faster, more powerful alternative specifically designed to replace filter branch with better performance and usability. Second, BFG repo cleaner. It is optimized for removing unwanted data like large files or credentials from Git history, and it's much faster than filter branch. Third, Git rebase interactive mode. This is for simpler history rewrites on smaller ranges of commits. Interactive rebase can be more straightforward. Here are the key takeaways. Filter branch is powerful but slow for rewriting Git history at scale. Use it for removing sensitive data, changing author information, or extracting subdirectories. Always back up your repository before running filter branch. Consider modern alternatives like Git filter repo for better performance. Rewriting history requires coordination with your team. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Git Filter Repo, a modern alternative to Git Filter Branch for rewriting history. Why use Git Filter Repo? Let's explore the advantages over Filter Branch. Git Filter Repo offers much faster performance, a cleaner, more focused design, safer history rewriting, better handling of large repositories, and is recommended by Git maintainers. Now let's discuss some common use cases. Git Filter Repo can be used to remove sensitive data from history, extract subdirectories into new repos, rewrite commit messages or authors, clean up repository structure, and prepare for open sourcing projects. Installing Git Filter Repo. There are a few ways you can install Git Filter Repo on your system. Using pip, the Python package manager, you can run the command pip3 install Git Filter Repo. On macOS with Homebrew, use the command brew install Git Filter Repo. On Debian or Ubuntu, you can use the command apt-get install Git Filter Repo. Please note that Git Filter Repo requires Git version 2.24.0 or newer. Basic usage of Git Filter Repo. Always make a backup before using Filter Repo. You can do this by running the command git clone, mirror original repo backup repo. The basic syntax for using Git Filter Repo is Git Filter Repo, options. Here's an example of how to keep only a specific directory. Execute Git Filter Repo, path source/force. Important: Git Filter Repo rewrites history permanently. Always work on a fresh clone of your repository. Path filtering with Git Filter Repo. First, let's explore how to keep only specific paths. The command git filter repo, path source/ preserves only the source directory and its contents, removing everything else from the repository history. Next, let's see how to remove specific paths. The command git filter repo, invert paths, followed by pathconfig/secrets.yaml, and path credentials/ removes the specified paths from the entire repository history. This is useful for removing sensitive data. Changing author information in Git. Here is how to perform email and name replacement. To replace a specific email address, use the command git filter repo, email callback, followed by return email if email is not equal to old@example.com else new@example.com. To create a mail map file for multiple replacements, first, create a file named mailmap.txt and add lines of the form. New name less than new@example.com greater than old name less than old@example.com greater than, and Jane Doe less than Jane@company.com greater than less than Jane@gmail.com greater than. Then, run the command git filter repo mailmap.txt. These commands help you update author and committer information throughout the repository history, which is useful when migrating repositories or updating personal information. Rewriting commit messages with Git Filter Repo. Here's how to modify messages. To replace text in all commit messages, use the command git filter repo message callback, followed by return messaged, replace open parenthesis, quote typo, quote comma, quote spelling error, quote close parenthesis. To add a prefix to all commit messages, use the command git filter repo message callback, followed by return quote open square bracket project, -123 close square bracket quote plus message, if not message, starts with open parenthesis quote open square bracket project, -123 close square bracket quote close parenthesis else message. These commands are useful for standardizing commit messages across a project, adding ticket references, or removing sensitive information that might have been accidentally included in commit messages. Advanced filtering techniques with Git Filter Repo. Let's explore file content filtering. Use the command git filter repo, blob callback followed by the string, if b quote API underscore key quote in data colon return data. Replace open parenthesis b quote API underscore key equals ABC123 quote comma, be quote API underscore key equals removed quote close parenthesis return data. This modifies file contents throughout history to remove sensitive data like API keys or passwords. Now let's explore date manipulation. The command git filter repo, commit callback followed by the string import time, commit.author_date equals commit_author_date minus 7 * 24 * 60 * 60, commit.committer_date equals committer_date minus 7 * 24 * 60 * 60, return commit, adjust commit timestamps, which is useful for correcting time zone issues or shifting project timelines. Best practices when using Git filter repo. Always work on a fresh clone of your repository. Create a backup before starting using the command git clone mirror. Test your commands on a small repository first. Coordinate with team members before force pushing changes. Document the commands you used for future reference. Use ~dry run when available to preview changes. For further resources, refer to the official documentation at github.com/ini-ren/git-filter-repo and the Git SCM book at git-scm.com/book. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. In this video, we're going to explore the Git bundle command, a powerful feature for moving Git repositories without needing a remote server. Let's dive in and discover how this tool can simplify your workflow. A Git bundle creates a single file. This file contains all the data needed to recreate a repository's branches, commits, and files. This feature is useful to transport Git data without a remote server. It saves the complete repository history in a single file and is perfect for offline collaboration. The Git bundle command is useful in a number of scenarios. First, when there is no internet connection and you need to transfer Git repositories between systems without network access, or when internet connectivity is limited or unreliable. Second, when working in high-security environments where external Git hosting services are blocked or not permitted due to compliance requirements. Third, create portable backups of your Git repositories that include all history, branches, and tags in a single file that can be easily archived. Finally, it efficiently bootstraps new team members with a complete repository history without requiring them to clone large repositories over slow connections. To create a bundle, use the command git bundle create, followed by the output file name and the references you want to include. To bundle all branches, run the command git bundle create repo.bundle all. To bundle specific branches, run the command git bundle create repo.bundle main develop. To bundle with tags, run the command git bundle create repo.bundle all tags. As a pro tip, for incremental bundles, you can specify a range of commits using the revision syntax. This is useful for creating smaller update bundles. Before using a bundle, it's good practice to verify its contents and integrity. To list the references contained in the bundle, run the command git bundle verify repo.bundle. The verify command checks if the bundle is valid and can be applied to the current repository. It lists all references like branches and tags contained in the bundle. If the bundle is corrupt or incomplete, Git will display an error message. There are two scenarios to consider here. First, creating a new repository. Clone directly from a bundle file to create a new repository by running the command git clone repo.bundle new repo. After this, navigate to the new repo by running cd new repo. The bundle file acts as a complete Git repository, containing all history and references specified during creation. Second, updating an existing repository. Pull changes from a bundle into an existing repository by running the command git remote add bundle-remote repo.bundle. After this, fetch from the bundle by running git fetch bundle-remote. Then merge changes by running the command git merge bundle-remote /main. For large repositories, you can create incremental bundles that only include changes since a specific commit. To create an incremental bundle with changes since v1.0 tag, run the command git bundle create incremental bundle v1.0 to main. To create bundle with changes in the last 10 commits, run the command git bundle create recent bundle main ~temp main. The workflow is: first create a complete bundle with all history for the first transfer. Then note the latest commit hash or tag that was included in the previous bundle. Finally, create smaller bundles containing only new commits since the base point. Here are a few best practices to consider. Always verify bundles before using them to ensure integrity. Use descriptive file names that include date and branch information. For large repositories, use incremental bundles to reduce file size. Document which commits are included in each bundle, and consider compressing large bundles with gzip or zip. To summarize, Git bundle creates a portable file containing repository data. It is useful for offline collaboration and repository transfer. It can create complete or incremental bundles. Bundles can be used like Git remotes and are perfect for air-gap environments or limited connectivity. Git bundle, a powerful tool for portable Git repositories. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. Welcome to Git Archive, a guide on creating archive files from Git repositories. In this session, you'll learn how to export snapshots of your Git repository as compressed archive files, such as zip, tar, and tar.gz, without including any of the Git metadata. Let's start with the basics of Git Archive. Git Archive creates a compressed archive of files from a specified tree, excluding Git metadata. This tool is useful for creating a snapshot of your repository, excluding the .git directory and metadata, making it ideal for creating release packages. It supports multiple archive formats and can archive specific commits or branches. Here are some examples of how to use Git Archive. To create a tar archive of the current head, use the command git archive format equals tar, then specify head, then redirect to project.tar. To create a zip archive of the master branch, use the command git archive format equals zip, then specify master, then redirect to project.zip. To create a compressed tar archive, use the command git archive format equals tar.gz, then specify head, then redirect to project.gz. Now let's explore some advanced options for Git Archive. The format option allows you to specify the archive format such as tar, zip, or tar.gz. The prefix option lets you prepend a path prefix to each file name in the archive. The remote option allows you to retrieve the archive from a remote repository. With the output option, you can write the archive to a specified file. The worktree attributes option allows you to read Git attributes from the working tree. Here are some examples of how to use these options. To add a project -1.0/prefix to all files, use the command git archive prefix equals project -1.0/-o release.zip, then specify head. To archive only specific directories or files, use the command git archive format equals tar, then specify head, then specify source/ and doc/ and redirect to partial.tar. To archive a specific tag with the output option, use the command git archive format equals zip --output equals v1.zip, then specify v1. To archive from a remote repository, use the command git archive remote equals git at github.com:user/repo.git, then specify head. Git allows you to filter which files are included in your archives using .git attributes and path specifications. You can use export-ignore to exclude files from archives, and export-substitute to expand Git attributes in files. Patterns work similarly to .git ignore. Here's an example of a .git attributes file. To exclude test files and documentation from archives, add the following lines to your .git attributes file: test/export-ignore, docs/export-ignore, .gitignore export-ignore, and readme.md export-substitute. You can also use path specification to archive only the source directory by using the command git archive, format equals zip, then specify head, then source/o source-only.zip. To exclude specific file types, use the command git archive head, format equals tar, double hyphen, dot, colon, exclamation mark asterisk dot log, and redirect to no-logs.tar. Let's look at some practical examples of using Git archive. To create a version release archive with a proper directory structure, use the command git archive, prefix equals myApp-1.0/-o myApp-1.0 then specify v1.0. To create an archive from a specific commit in history, use the command git archive, format equals zip, -o bugfix.zip, then specify a 1b2c3d4. To create compressed archives with different formats, use the command git archive, format equals tar head, pipegzip, and redirect to project2ez. Or use the alternative direct method, git archive, format equals tar gz head, -o project.gz. To archive only source files, use the command git archive, format equals zip head, source/lib/-o source.zip. Git archive is a powerful tool for creating deployment packages in continuous integration and deployment workflows. Common continuous integration continuous deployment use cases include automated release package creation, deployment artifact generation, clean source code distribution, version-specific deployments, and environment-specific package creation. Here's an example of how to use Git archive in a GitHub Actions workflow. The workflow is triggered on push to tags that match the pattern v*. The workflow checks out the code, then creates a release archive using the command version equals GitHub_reference number sign ref/tags/ and git archive, prefix equals $version /-o $version.zip head. Here are some best practices to keep in mind when using Git archive. Always use .git attributes to control what gets archived. Include version information in archive file names. Use the prefix option to create a proper directory structure. Archive from tags for reproducible releases. Automate archive creation in continuous integration continuous deployment pipelines. Choose the appropriate compression format for your needs. Test archives before distribution to ensure completeness. Git archive is a powerful tool for creating clean snapshots of your repository without Git metadata. It's ideal for creating release packages, deployment artifacts, and distributing source code. Key features include format selection, content filtering, and integration with continuous integration continuous deployment pipelines. For further resources, refer to the Git documentation at git-scm.com/docs/git-archive and the Pro Git book at git-scm.com/book. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. In this video, let's explore Git Rerear, a powerful tool that can significantly streamline your workflow when dealing with merge conflicts. Rerear stands for Reuse Recorded Resolution. It's a Git feature that automates conflict resolution by remembering how you resolved similar conflicts in the past. This is especially useful for long-lived feature branches, rebusing complex branches, and repetitive merge operations. So, what exactly is Git Rerear? Rerear stands for Reuse Recorded Resolution. It is a Git feature that remembers how you resolved a merge conflict and automatically applies the same resolution when Git encounters the same conflict again. This is especially useful for long-lived feature branches, rebusing complex branches, and repetitive merge operations. When enabled, Git will first record the pre-image of a conflict, Second, record your conflict resolution, and third, apply the recorded resolution automatically when the same conflict appears again. To enable Git Rerear, use the command git config --global rerear.enabled true. Why should you use Git Rerear? It offers several key benefits. Firstly, it saves time. Resolve complex conflicts only once, and let Git handle them automatically in the future. This is particularly valuable when working with long-lived feature branches that need frequent rebasing. Secondly, it ensures consistent resolutions, ensuring that the same conflicts are resolved in the same way every time, maintaining consistency across your codebase, and reducing the chance of introducing errors. Thirdly, it reduces mental overhead. There is no need to remember how you resolved specific conflicts in the past. Git remembers for you, allowing you to focus on new challenges rather than solving the same problems repeatedly. Lastly, it simplifies complex workflows, making rebasing, cherry-picking, and merging much less painful in complex projects with multiple branches and frequent integration points. It is perfect for teams with feature branch workflows. Let's see how to enable Git Rerear. You can configure it globally for all repositories on your system using the command git config --global rerear.enabled true. You can verify if it is enabled or not by running the command git config --global rerear.enabled. As a pro tip, add this to your .files or setup scripts to ensure Rerear is always enabled on new systems. You can also enable Rerear for a specific repository only. Navigate to your repository, then use the command git config rerear.enabled true. Alternatively, you can create the Rerear directory manually. Rerear data is stored locally and not pushed to remote repositories. Each developer needs to enable it separately. Let's understand how Git Rerear works. When a merge conflict occurs, Git Rerear records the state of the conflicted file before any resolution. This is stored in .git/r-cache as the pre-image of the conflict. After you manually resolve the conflict and stage the file, Git Rerear records your resolution. This post-image is stored alongside the pre-image, creating a resolution pattern. When the same conflict pattern appears again, Git Rerear recognizes it and automatically applies your previous resolution. You will see a message resolved file name using previous resolution. Git Rerear only records resolutions. It doesn't automatically commit them. This gives you a chance to review the automatic resolution before committing. Let's walk through a basic usage example. When you encounter a conflict for the first time, Rerear records the resolution. Create a merge conflict using the command git merge feature branch. Resolve the conflict manually in your editor. Then stage the resolved file using the command git add file name. Finally, complete the merge using the command git commit-m merge feature branch. Git Rerear silently records your resolution in the background. No additional commands needed. The next time you encounter the same conflict, it is automatically resolved. Create the same conflict again using the command git merge another branch. Git Rerear automatically applies the resolution. You will see the message resolved using previous resolution. Git has automatically applied your previous conflict resolution. Verify and complete the merge by using the commands git add, file name, and git commit-m merge another branch. Let's delve into some advanced usage of Git Rerear. To view recorded conflicts, list all conflicts that Git Rerear has recorded using the command git rerear status. You can also show detailed difference of recorded resolutions using the command git rerear diff. To clear recorded resolutions, you can remove specific or all recorded conflict resolutions using the command git rerear clear to clear all recorded resolutions, or git rerear forget file name to forget resolution for a specific file. Rerear is especially useful during complex rebases. Start an interactive rebase using the command git rebase-i main. When conflicts occur, Git Rerear will automatically apply recorded resolutions. You can configure Git to automatically stage files resolved by rerear by enabling auto-staging of resolved files using the command git config --global rerear.autoupdate true. Here are some best practices to keep in mind when using Git rerear. Always review resolutions. Even though Git rerear automatically applies resolutions, always review them before committing. Context may have changed since the original resolution. Enable it in continuous integration and continuous delivery pipelines. For automated workflows, enable rerear in your continuous integration and continuous delivery pipelines to handle repetitive conflicts in automated merges and integration tests. Consider sharing resolutions with your team. Share the .git/r-cache directory with your team for complex projects. This can be done via a separate repository or shared storage. Clean up periodically. Use Git rerear clear periodically to remove outdated conflict resolutions, especially after major refactoring that changes conflict patterns. Verify with rerear status. Use Git rerear status and Git rerear diff to inspect what resolutions Git has recorded and will apply in future conflicts. Combine with Git aliases. Create Git aliases for common rerear workflows to streamline your conflict resolution process and make the commands more memorable. In summary, Git rerear remembers and automatically reapplies your conflict resolutions, saving time and ensuring consistency. Enable it with git config --global rerear.enabled true for all repositories. It works silently in the background, recording resolutions as you resolve conflicts normally. Use Git rerear status and Git rerear diff to inspect recorded resolutions. Manage recorded resolutions with Git rerear clear and Git rerear forget. Always review automatically applied resolutions before committing to ensure they still make sense. For further resources, you can refer to Git documentation on Git-rerear, Pro Git Book, Chapter 7.9, and Git Software Configuration Management website, git-scm.com. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Let's explore Git Notes. Git Notes are used for adding metadata to commits without changing the commit history. They allow you to attach extra information to your commits, making it easier to track reviews, builds, or other important details. Git Notes provide a way to add or edit metadata for Git objects, without changing the objects themselves. Git Notes allow you to annotate commits with additional information without altering commit history. Let's explore some key features. First, Git Notes are stored separately from commits. Second, Git Notes can be shared between repositories. Third, Git Notes don't affect commit hashes. Fourth, Git Notes can be added retroactively. Here are some common use cases for Git Notes. First, code review feedback. You can store detailed code review comments and feedback that are too extensive for commit messages, but important for historical context. Second, CI/CD information. Attach build results, test outcomes, and deployment information to specific commits without modifying the commit itself. Third, issue tracking. Link commits to issue trackers or add references to external systems and documentation after the commit was created. Fourth, performance metrics. You can record performance benchmarks or metrics associated with specific code changes to track optimization efforts over time. Let's explore basic Git Notes commands. First, how to add notes. You can attach a note to a commit using the command git notes add. You can specify the commit or use head for the most recent commit. To add a note to the most recent commit, use the command git notes add -m followed by the message in quotes like this fix bug number 123 in quotes. To add a note to a specific commit, use the command git notes add -m followed by the message in quotes like important fix in quotes, followed by the commit ID, a 1B2C3D4. Next, how to view notes. You can view notes attached to commits using Git log with the Show Notes option, or view a specific commit's notes. To show all commits with their notes, use the command git log -show-notes. To view notes for a specific commit, use the command git notes show, followed by the commit ID, A1B2C3D4. Let's explore advanced git notes commands. First, how to edit notes. You can modify existing notes attached to a commit. This replaces the previous note content with new content. To edit the note on the current commit, use the command git notes edit. To edit the note on a specific commit, use the command git notes edit, followed by the commit ID, A1B2C3D4. Next, how to remove notes. You can delete notes that are no longer needed from specific commits without affecting the commit itself. To remove a note from the current commit, use the command git notes remove. To remove a note from a specific commit, use the command git notes remove, followed by the commit ID, A1B2C3D4. Let's explore working with git notes namespaces. Git notes can be organized into different namespaces, allowing multiple sets of notes to be attached to the same commit. This is useful for separating different types of metadata. The default namespace is commits if none is specified. To add a note in a custom namespace, use the command git notes --ref equals code -review add -m, followed by the message in quotes, LGTM in quotes, followed by the commit ID, A1B2C3D4. To view notes in a specific namespace, use the command git notes --ref equals code -review show, followed by the commit ID, A1B2C3D4. To list all namespaces, use the command git notes list. To remove a note from a namespace, use the command git notes --ref equals build -info remove, followed by the commit ID, A1B2C3D4. Let's explore how to share git notes. Git notes are not automatically pushed or pulled with regular commits. You need to explicitly push and pull notes to share them with others. To push notes to a remote repository, use the command git push origin refs /notes /**. To push notes from a specific namespace, use the command git push origin refs /notes /code -review. To pull notes from a remote repository, use the command git fetch origin refs /notes *refs /notes /*. To pull a specific namespace, use the command git fetch origin refs /notes /build refs /notes /build. You can configure Git to automatically push and pull notes with regular commits. To configure automatic notes fetching, use the command git config --add remote.origin fetch refs /notes *refs /notes *. Note that this only configures fetching. For pushing, you'll need to set up a push ref spec or use explicit push commands. Let's explore some Git notes best practices. First, use structured formats. Consider using structured formats like JSON or YAML for notes content to make it machine-readable and consistent. Second, namespace organization. Use different namespaces for different types of metadata, for example, code review, build info, deployment. Third, document your workflow. Document your team's notes usage and sharing conventions to ensure everyone follows the same practices. Fourth, avoid sensitive information. Don't store secrets or sensitive information in notes, as they can be easily shared between repositories. Git notes provide a powerful way to annotate your repository history without changing commit hashes, enabling better documentation and metadata tracking. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content. Welcome! In this video, we'll explore Git debugging techniques. We will see how to troubleshoot common Git problems effectively. Let us get started. Let us examine some common Git issues and debugging approach. Common Git issues include merge conflicts, detached head state, accidental commits, lost changes, and authentication failures. To debug, first check the Git status. Then review the Git log history. Examine the ref log for lost commits, use git config to verify settings, and read error messages carefully. Merge conflicts occur when Git can't automatically reconcile differences between branches. To resolve the conflicts, first identify the conflicting files. Understand conflict markers. Then, edit files to resolve conflicts and mark them as resolved with the git add command. Here's an example of how a conflict appears during a merge. Running the command git merge feature branch results in a merge conflict in file.txt. The conflict markers in the file will look like this. O of head, current branch content, equals, incoming branch content, and O feature branch. After resolving the conflicts, use the command git add file.txt, and then git commit mresolve merge conflict. A detached head occurs when you check out a specific commit instead of a branch. Your head points directly to a commit rather than a branch reference. Common causes include checking out a specific commit hash, checking out a tag, or using git checkout head 3. To detect a detached head, use the command git status. The output will show head detached at, followed by a commit hash, and the message you are in detached head state. To fix this, you can create a new branch using git branch new branch, and then git checkout new branch. Alternatively, you can create a branch and checkout in one step, using the command git checkout b recovery branch. To return to the previous branch, use git checkout main, and merge if needed with git merge recovery branch. Sometimes you need to undo mistakes in Git. To discard changes in the working directory, use git checkout file.txt. To unstage a file while keeping the changes, use git restore staged file.txt. To discard all changes, use git reset hard head. Warning: this cannot be undone. To stash changes temporarily, use git stash and git stash pop to restore them later. To amend the most recent commit, use git commit amend. To revert a commit and create a new commit, use git revert head. To undo the last commit while keeping the changes, use git reset head 1. To undo multiple commits, use git reset head 3. For more complex history editing, use interactive rebase with git rebase I head 5. Git's reflog tracks all reference changes in your local repository, including commits that are no longer referenced, branch deletions, reset operations, and rebases and merges. Reflog entries expire after 90 days by default, or 30 days for unreachable commits. To view the reflog history, use the command git reflog. This will display a list of commits with their corresponding head references. To recover a lost commit, use git checkout followed by the commit hash. Then create a new branch with git checkout b recovery branch. To recover after a hard reset, use git reflog to find the appropriate head reference and then use git reset hard head at 1. To find a deleted branch tip, use git reflog and grep for the branch name. Let us discuss troubleshooting authentication issues. Common authentication problems include permission-denied public key errors, invalid username or password credentials, expired personal access tokens, an SSH key not registered with remote, a wrong remote URL protocol, such as HTTPS versus SSH, and credential helper issues. To solve these problems, verify the remote URL with the command git remotev. Update credentials using git credential manager. Test the SSH connection with the command sshttgit at github.com. Update the remote URL protocol using git remote set URL origin, followed by the URL. Generate a new SSH key using sshkeygen at 25519. Use credential caching by configuring git config credentialed helper. Git provides several advanced tools to help diagnose complex issues. These include Git Bisect for finding bugs, Git Blame for tracking changes, Git Debug for verbose output, Git FSCK for repository integrity, and Git GC for repository optimization. To find which commit introduced a bug, use Git Bisect Start, Git Bisect BAT to indicate the current commit has a bug, and Git Bisect Good version 1.0 to indicate that version 1.0 was working. Git will check out commits to test. Use Git Bisect Good or Git Bisect Bad as needed, and then Git Bisect Reset when done. To find who changed a line and when, use Git Blame L1020 file.txt. To check repository integrity, use Git FSCK full. Let us examine fixing Git performance issues. Common performance problems include slow clone, fetch and pull operations, repository bloat from large files, too many objects in the working directory, inefficient hooks or filters, an excessive number of refs, such as branches or tags, and network bandwidth limitations. To optimize performance, use a shallow clone for large repos with the command git clone, depth equals 1. Clean up with garbage collection using git GC aggressive. Use sparse checkout for large repos with the command git sparse checkout set followed by the directory. Prune unnecessary remote tracking using git fetch, prune. Configure git LFS for large files with git LFS install. Use partial clone with git clone, filter equals blob, none. Here are some Git debugging best practices. For prevention, commit small, focus changes, write clear commit messages, pull before pushing changes, use feature branches, set up pre-commit hooks and configure .git ignore properly. For diagnosis, check the Git status first, read error messages carefully, use Git log to understand history, examine the ref log for recent actions, try the verbose flag for more info, and use Git Bisect for finding bugs. For recovery, create backups before major changes, use Stash to save work in progress, know how to use reflog for recovery, practice safe rebase techniques, understand reset versus revert, and document complex workflows. Remember, Git never truly loses your work. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Welcome to this presentation on Git performance optimization. In this session, we will explore strategies and techniques for improving performance in large Git repositories. Let's dive in. Let's discuss common performance challenges encountered in large Git repositories. Performance issues include slow clone and fetch operations, delayed checkout and branch switching, sluggish status and log commands, high memory consumption, and excessive disk space usage. To counter these, we have optimization areas like repository structure optimization, Git configuration tuning, workflow adjustments, advanced Git features utilization, and server-side optimizations. Two useful techniques to reduce the amount of data transferred and improve the speed of Git operations are shallow clones and partial clones. A shallow clone retrieves only the recent commit history, which reduces the clone size and time. You can perform a shallow clone using the command git clone, depth equals 1 followed by the repository URL. If needed, you can fetch more history later using the command git fetch, unshallow. A partial clone filters out large files during the clone process, downloading them only when needed. You can clone without blob objects using the command git clone, filter equals blob, none followed by the repository URL. Optimizing Git configuration can significantly improve performance. To speed up status operations, set your core.untracked cache to true using the command git config global core untracked cache true. To enable parallel index preload for operations like status, set core.preloadIndex to true using the command git config global core.preloadIndex true. To utilize multiple threads when packing repositories, set pack.threads to 0 using the command git config global pack.threads 0. Git Large File Storage, or LFS, is an extension that stores large files outside the Git repository, using pointers inside the repository. To install and set up Git LFS, use the command git lfs install. To track large file types, use the command git lfs track, followed by the file extension, such as star.psd or star.zip. Sparse checkout allows you to check out only specific directories, reducing the working tree size. To enable sparse checkout, use the command git sparse checkout init. To specify the directories to include, use the command git sparse checkout set, followed by the directory paths, such as src/main and docs. Regularly cleaning up and optimizing your repository can improve performance. Standard garbage collection can be performed using the command git gc. For a more thorough cleanup, use the aggressive garbage collection option with the command git gc aggressive. To remove unreachable objects older than 2 weeks, use the command git prune. Let's explore some advanced optimization techniques. Submodules and subtrees involve splitting large repositories into smaller, more manageable ones, referencing external repositories. This approach can improve performance by working with smaller code bases. To add a submodule, use the command git submodule add, followed by the repository URL. Server-side optimizations can also greatly enhance performance. Enable Git Protocol version 2 to improve data transfer efficiency. Configure server-side hooks for maintenance tasks. Use reference repositories for shared objects, and implement Git caching proxies to speed up access. To enable Protocol version 2 on the client side, use the command git config global protocol.version 2. Several tools can help you identify performance bottlenecks in your Git workflow. GitSizer computes various size metrics for a Git repository and warns about excessive repository bloat. GitTrace2 is a built-in performance tracing framework for analyzing Git command execution. BFG Repo Cleaner removes large or problematic files from Git history. Git Filter Repo is a powerful tool for rewriting repository history and removing unwanted data. Here are some best practices for Git performance optimization. Consider monorepo versus multi-repo strategies based on your team's needs and codebase size. Schedule routine repository maintenance to prevent performance degradation. Use Git LFS or external artifact repositories for large binary files. Regularly benchmark Git operations to catch performance regressions early. Optimizing Git performance is an ongoing process that requires a combination of proper configuration, workflow adjustments, and regular maintenance. The techniques covered in this presentation can significantly improve your experience with large repositories. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Welcome to this session on Git best practices. In this video, we'll cover guidelines for effective Git usage to help you and your team work more efficiently and maintain a cleaner, more organized code repository. So, why should you follow Git best practices? For teams, it improves collaboration efficiency, reduces merge conflicts, maintains a clean project history, and simplifies code reviews. For individuals, it's easier to track changes, simplifies the debugging process, improves workflow organization, and builds professional habits. One of the most important Git best practices is writing meaningful commit messages. Let's see some examples. A good commit message has a concise title and a detailed description. For example, a good commit message would be, feat, add user authentication system, followed by a description that says, implement JSON Web Token generation, add login or logout endpoints, and create middleware for route protection. On the other hand, a poor commit message looks like fix stuff with the description, updated code. It doesn't explain what was fixed or updated. Let's dive into conventional commits. The format helps categorize changes and improves readability. The format is type, scope, description. Common types are feature, which introduces a new feature. Fix, which resolves a bug. Docs, which makes changes to documentation. Style, which improves code style and formatting. Refactor, which refactors code without adding a feature or fixing a bug. Test, which adds or modifies tests. Chore, which involves maintenance tasks. Next, let's explore an effective branching strategy called Git flow. The key branches include the main or master branch, which contains production-ready code. The develop branch, which has the latest development changes. Feature/star, which contains new features. Hotfix/star, which is for urgent production fixes. Release/star, which is used for preparing releases. Some common commands include git checkout-b feature/login, git checkout develop, git merge feature/login, and git branch-d feature/login. Creating effective pull requests is crucial for code review. Keep your pull requests small and focused on a single task. Include clear descriptions of changes, link to relevant issues or tickets, add screenshots for user interface changes, and include testing instructions. For the pull request review process, request reviews from appropriate team members, address all comments before merging, use draft pull requests for work in progress, ensure continuous integration checks pass before merging, and use squash merging for cleaner history. Good pull requests facilitate effective code reviews and maintain code quality. Let's look at how to keep your Git history clean by rewriting it. One way to do this is with interactive rebase. Use the command git rebase-i head -3. In the editor, you can pick, squash, or reword commits. Use interactive rebase to combine, edit, or reorder commits. Another way is to amend commits. Edit your files, then use the command git add period, followed by git commit double-amend. To change only the message, use the command git commit double-amend-m, followed by a new message. Only amend commits that haven't been pushed to shared branches. An important part of managing your project is an effective .git ignore configuration. Consider what files to ignore. These include build artifacts and compiled code, dependency directories such as node modules and vendor, environment files with secrets, such as .environment, IDE configuration files, such as .idea and .versus code, and log files and temporary data. An example of a .git ignore file looks like dependencies/node modules/vendor build output/dist/build, environment variables, .environment.local IDE files, /idea, /versus code. Git hooks allow you to enforce standards with automation. Some common client-side hooks include pre-commit, which can run linters, formatters, and tests. Commit message, which validates commit message format. Pre-push, which runs comprehensive tests, and prepare commit message, which auto-generates commit templates. Here's an example of a pre-commit hook. This script runs code linting using npm run lint. If linting fails, it exits with an error. Then it runs tests using npm test. If tests fail, it exits with an error. In summary, here are the key takeaways for effective Git usage. Write clear, descriptive commit messages following conventional formats. Use a consistent branching strategy like Git flow for team collaboration. Create focused pull requests with comprehensive descriptions. Maintain a clean commit history using rebase and amend. Configure a proper .git ignore to exclude unnecessary files. Implement Git hooks to automate quality checks. Consistent application of these practices improves team productivity and code quality. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Welcome to the presentation on Git security best practices. In this session, we will explore how to secure your Git workflow and repositories, ensuring the safety and integrity of your code. Let's examine some common security threats associated with Git. These include sensitive data exposure within the commit history, unauthorized access to repositories, malicious code injection, insecure dependencies, and weak authentication mechanisms. Being aware of these threats is the first step in protecting your Git environment. Now let's delve into authentication and access control. It's best to use Secure Shell, or SSH, keys instead of passwords for authentication. Enable two-factor authentication, also known as 2FA, for an extra layer of security. Regularly rotate access tokens, implement fine-grained access controls, and audit access permissions regularly to maintain a secure Git environment. Here's an example of how to set up SSH authentication. First, generate a new SSH key using the command ssh-keygen -t at 25519-c, followed by your email address. Next, start the SSH agent with the command eval, open parenthesis, $ssh-agent, -s, close parenthesis. Then, add your SSH key to the agent using the command ssh-add, followed by the path to your SSH key file. Finally, copy the public key to your clipboard using the command cat, followed by the path to your public key file. Let's explore how to prevent sensitive data exposure in Git. Accidentally committing sensitive data is a common security issue. Use a .gitignore file to exclude sensitive files from being tracked. Implement pre-commit hooks for validation. Store secrets in environment variables, and use secret management tools to protect sensitive information. Here's an example .gitignore file for security. We are ignoring configuration files with secrets, private keys and certificates, and credential files. Make sure to adjust these patterns according to your needs. Let's discuss Git secrets and pre-commit hooks. Utilize tools like Git secrets to prevent committing sensitive information to your repositories. These tools scan commits for Amazon Web Services, or AWS, keys, passwords, and other secrets, blocking commits that contain such information. Git Secrets offers customizable patterns for detection and integrates seamlessly with continuous integration and continuous delivery, or CI/CD pipelines. To set up Git Secrets, first install it. Then, initialize Git Secrets in your repository. Finally, register AWS patterns and add any custom patterns as needed. Now let's explore signed commits and tags, which provide cryptographic proof of the author of the code, preventing impersonation attacks. Signed commits and tags ensure commit authenticity, prevent commit spoofing, build trust in collaborative projects, and are often required by security-focused teams. To set up Pretty Good Privacy or GPG signed commits, generate a GPG key. List your GPG keys to identify the key ID. Configure Git to use your key and enable signed commits by default. Let's move on to branch protection and code reviews for securing your workflow. Implementing branch protection rules prevents unauthorized changes and ensures code quality. We can require pull request reviews, enforce status checks before merging, require signed commits, restrict who can push to protected branches, and prevent force pushes to critical branches. Here's an example of a GitHub branch protection configuration file. Protection specifies the branch protection settings. Required_status_checks specifies that the status checks must pass before a branch can be merged into. Required_pull_request_reviews specifies the number of approvers required and whether stale reviews should be dismissed. Enforce_admins indicates whether administrators are also subject to these rules. Required_signatures specifies that all commits on the branch must be signed. Let's delve into dependency security. Third-party dependencies are a common attack vector. Implement tools to detect and mitigate vulnerable dependencies. It's important to regularly scan dependencies for vulnerabilities, set up automated dependency updates, use dependency lock files, implement dependency pinning, and validate dependency sources. For JavaScript projects, utilize npm audit. With GitHub, you can use Dependabot to automate dependency updates. The version key specifies the version of the Dependabot configuration file. The updates key specifies the packages to update. Package ecosystem specifies the package manager to use. Directory specifies the location of the package manifest file. Schedule specifies how often to check for updates. In summary, here's a checklist of key security practices to implement. For authentication, use Secure Shell, or SSH, keys and enable two-factor authentication, also known as 2FA. In terms of secrets management, never commit sensitive data. Use signed commits to verify code authenticity. Implement branch protection to enforce code reviews. Utilize scanning tools to detect vulnerabilities early. And automate processes by implementing pre-commit hooks. Remember, security is a continuous process, not a one-time implementation. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Welcome. This presentation is on Git for DevOps, focusing on integrating Git in DevOps practices and pipelines. We will explore the benefits and methods of using Git to enhance version control, continuous integration and continuous delivery integration, automation and collaboration within DevOps environments. Let's discuss why Git is important in DevOps. First, it offers version control for infrastructure as code, enabling you to manage and track changes to your infrastructure configurations just like application code. Git enables collaboration across development and operations teams, providing a centralized platform for code sharing and joint efforts. It provides traceability and audit trails for all changes, so it is easier to track who made what changes and when. Finally, it facilitates automated testing and deployment, which is a crucial component of continuous integration and continuous delivery pipelines. Here are some essential Git commands that are beneficial in a DevOps environment. In the area of repository setup and management, Git init creates a new Git repository. Git clone downloads a repository from a remote location. Git remote add origin links your local repository to a remote repository. In the workflow commands section, Git status shows the status of your working tree, so you can see what files have been modified. Git add stages all changes for commit. Git commit m records changes to the repository with a descriptive message. Lastly, Git push origin main uploads local commits to the remote repository. In this slide, let's explore branching and merging, which are essential aspects of managing code in a DevOps workflow. First, let's look into branch management. The Git branch feature login command creates a new branch. To switch to a branch, use Git checkout feature login. As a shorthand, you can create and switch to a new branch using Git checkout b hotfix auth. To list all available local branches, use Git branch. Now let's look into merging and integration. The Git merge feature login command merges the specified branch into the current branch. Git rebase main reapplies commits on top of another branch. In case of conflicts, use Git merge tool to open a visual tool to resolve them. Lastly, Git branch d feature login deletes a branch after it has been successfully merged. Let's explore two common Git workflow models used in DevOps. Gitflow uses multiple long-lived branches with specific roles, which is ideal for projects with scheduled releases and versioning. Trunk-based development, on the other hand, uses short-lived feature branches merged frequently to main. This is more suitable for continuous delivery and integration practices. Now let's discuss how to integrate Git with continuous integration and continuous delivery pipelines using some examples. Here is an example of a Jenkins pipeline defined in a Jenkins file, which specifies stages such as checkout and build. Here is an example of a GitHub Actions workflow, which defines jobs that run on pushes to specific branches, automating the build process. Here are some of the recommended Git practices for DevOps teams, starting with repository management. Always use a .gitignore file properly to exclude build artifacts, dependencies, and sensitive files from your repository. Also, implement Git hooks for linting and testing before commits. If dealing with large files, use Git Large File Storage, also known as LFS, for binary files and other large assets. In terms of collaboration practices, make sure everyone writes meaningful commit messages following a conventional format for clarity. Enable pull request reviews, enforcing code reviews before merging into main branches. Also, configure branch protection rules for critical branches and encourage everyone to create small, focused commits that address a single concern. Here are some advanced Git tools that can enhance productivity and streamline DevOps workflows. Git Large File Storage efficiently manages large files by storing file pointers in the repository, rather than storing the entire file. Git hooks are scripts that run automatically on specific Git events, such as commits and pushes. Git submodules allows embedding one repository inside another, which is useful for managing dependencies. For DevOps integration, Husky simplifies Git hooks management in JavaScript projects, Git version generates semantic versioning based on Git history, and Precommit is a framework for managing multi-language precommit hooks. Here are real-world examples of how companies use Git in DevOps practices. Netflix uses trunk-based development and feature toggles, resulting in thousands of deployments per day with minimal disruption. Etsy defines all infrastructure and code, stored in Git, resulting in over 50 deployments per day with a complete audit trail. To conclude, Git is a foundational tool for modern DevOps practices, enabling effective branching strategies for continuous integration and continuous delivery. Infrastructure as code benefits greatly from Git's version control capabilities. Automation and integration with continuous integration and continuous delivery pipelines maximize Git's value. To further your learning, refer to the Pro Git book, the official Git documentation, the GitLab DevOps Guide, and Atlassian Git tutorials. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this presentation, we'll explore the process of migrating from other version control systems to Git. Specifically, we will focus on converting repositories from Subversion, Mercurial, and other version control systems to Git. There are several compelling reasons to migrate to Git. First, a distributed workflow allows you to work offline with full repository history and commit locally before pushing changes. Second, branching and merging. Git's lightweight branches make feature development and experimentation easier. Third, performance. Git offers faster operations for most common version control tasks. Fourth, ecosystem and tooling. Git integrates extensively with modern continuous integration and continuous delivery. Finally, content addressable storage ensures data integrity through secure hash algorithm 1 hashing. Also, there is a large developer community and extensive documentation available. Effective migration requires careful planning. First, create an inventory of all repositories, branches, and tags. Second, choose appropriate migration tools based on the source version control system. Third, perform trial migrations with sample repositories. Fourth, prepare your team for Git workflow differences. Finally, migrate repositories with proper validation. Some key considerations include timeline or freeze periods during critical migrations, how much history to migrate, creating user mapping between the old version control system and Git, updating continuous integration and continuous delivery pipelines, and defining success criteria for migration verification. For Subversion to Git migration, Git provides a built-in tool called Git SVN that allows you to use Git as a client for a Subversion repository. The command is git svn clone, then the universal resource locator of the SVN repository, then /project, then standard layout, no metadata, authors file equals authors.txt, and local Git repository. To push to a new Git remote, use the command git remote add, then origin, then the universal resource locator of the Git repository. Then git push -u origin, then --all. Finally, git push origin, then --, tags. Subversion and Git have different approaches to repository organization. In Subversion structure, we have project, trunk, branches with feature 1 and feature 2 folders, and tags with version 1.0 and version 2.0 folders. In Git structure, we have project.git, and then main branch, feature 1 branch, feature 2 branch, version 1.0 tag, and version 2.0 tag. When migrating from Subversion to Git, author information needs to be converted from Subversion usernames to Git's name or email format to maintain proper commit attribution. First, extract all unique author names from your Subversion repository. Second, create an author's mapping file with Subversion username to Git name email pairs. Third, use the mapping file during Git SVN clone with the --authors file parameter. Finally, verify author information in Git history after migration. Here is the command to extract all unique authors from Subversion: subversion log, -q, pipegrep, !r, pipeawk, print $3, pipesort, -u greater than authors.txt. In the example authors.txt file format, we have username Smith equals John Smith within angular brackets, john.smith@example.com, username Jones equals Mary Jones within angular brackets, mary.jones@example.com, usernamed Kim equals David Kim within angular brackets, david.kim@example.com, username Ali equals Alice Lee within angular brackets, alice.lee@example.com. Use the Git SVN clone, the universal resource locator of the Subversion repository, --authors file equals authors.txt, -- standard layout, local Git repository command to include the authors file in your Git SVN command. Migrating large repositories comes with its own set of challenges. First, long migration times, as large repositories with extensive history can take days to migrate. Second, storage requirements, as Git stores complete history locally, requiring more disk space. Third, network bandwidth, as transferring large repositories can strain network resources. And fourth, large binary files in history can bloat repository size. Fortunately, there are solutions to these challenges. First, use Git's shallow clone to limit history depth with the command git svn clone -depth equals 100, then the universal resource locator for Subversion repository. Second, split large monolithic repositories with the command git subtree split -p path to folder -b split branch. Finally, use Git large file storage for large binary files with the commands git large file storage install and git large file storage track, zip, PDF, PSD. For Mercurial to Git migration, the fast export tool converts Mercurial repositories to Git format while preserving history, branches, and tags. The commands for this are git clone the universal resource locator for fastexport.git, then make directory git repository and change directory into it, git init, and then /fastexport/hg fastexport.sh-r the path to hg repository, then git checkout head. Mercurial's change set is git's commit. Mercurial's named branch is git's branch. Mercurial's bookmark is git's branch. Mercurial's tag is git's tag. Mercurial's hg update is git's git checkout. Mercurial's hg pull is git's git fetch. To migrate from Perforce to Git, Git provides a built-in tool called Git P4 that allows you to import Perforce repositories into Git while preserving history. The command to clone a Perforce depot is git p4 clone /depot/path/to/project et al. The command to import a specific change list range is git p4 sync /depot/path at 1000, 1500. And the command to submit changes back to Perforce is git p4 submit. For large repositories, consider using the --detect branches flag to properly convert Perforce branches. The command for this is git p4 clone /depot/path/ --detect branches. Key considerations for this migration include branching model. Perforce uses file paths for branches while Git uses references. Also, workspace mapping. Convert Perforce client specs to Git repository structure. Additionally, file locking. Git large file storage can provide similar functionality to Perforce file locking. Also, large binary files. Use Git large file storage for large binary assets common in Perforce repositories. Finally, create a mapping between Perforce users and Git authors. After migrating to Git, there are several essential tasks to perform. First, clean up the repository. Remove unnecessary files and optimize repository size. Second, update documentation. Update README and contribution guidelines for Git workflow. Third, configure continuous integration and continuous delivery. Update build pipelines to work with Git repository. Fourth, team training. Ensure team members are comfortable with Git workflows. Finally, access control. Set up proper permissions and access controls. Verification commands include git revlist, --count, --all to check the commit count matches the source repository. Also, git branch -a to verify all branches were migrated. Finally, check repository size with do-sh git, and clean up and optimize with git gc --aggressive. Here are some best practices to keep in mind. Always perform trial migrations with sample repositories. Schedule migrations during low activity periods. Keep detailed records of migration process and decisions. Consider migrating repositories in batches rather than all at once. Keep team members informed throughout the migration process. There are many helpful resources available, including Git source code management documentation, Git SVN manual, Git P4 documentation, the subject, fast export, and Git large file storage tools, and the Pro Git book. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this video, we will explore the differences between monorepo and multi-repo strategies for organizing your code. We'll compare these two approaches to help you understand which one might be the best fit for your projects. Let's dive in. Let's define each strategy. A monorepo is a single repository that contains multiple distinct projects with well-defined relationships. Key points include: all code lives in a single version control repository, projects may be related or unrelated, there's a shared build system and tooling, centralized dependency management and atomic commits across projects. In contrast, a multi-repo consists of multiple repositories, each containing a single project or a small group of tightly coupled projects. Key characteristics are: each project has its own repository, independent versioning and release cycles, project-specific build configurations, decentralized dependency management, and clear project boundaries and ownership. Let's visualize the structure of each approach. On the left, we have a monorepo structure. All projects such as front-end, back-end, mobile API, admin, and analytics reside within a single main repository. They share common libraries, components, build tools, and configuration. On the right, the multi-repo structure shows each project residing in its own separate repository. This includes front-end, back-end, mobile API, shared libraries, and analytics, each existing independently. Let's explore the benefits of each approach. Monorepo advantages include simplified code sharing and reuse with direct imports. Atomic changes can be made across multiple projects, ensuring consistency. There's consistent tooling and standards across all projects. Dependency management is simplified with a single version policy. It facilitates easier refactoring across project boundaries. There is a single source of truth for the entire code base, and it provides a unified continuous integration and continuous delivery pipeline for all projects. Multi-repo advantages include clear ownership boundaries between teams and projects. Independent versioning and release cycles are allowed. The code bases are smaller, more focused, and easier to understand. Build and test cycles are faster for individual projects. There's flexibility to use different technologies per project. There is a reduced risk of breaking changes affecting other projects, and it allows for better access control and security isolation. Now let's consider the challenges. Monorepo challenges include the repository size, which can grow very large, impacting clone times. Build times can become lengthy without proper tooling. It requires specialized tooling for efficient operation. Access control is more complex at the project level. Continuous integration and continuous delivery pipelines need to be optimized for incremental builds. There is potential for dependency hell with conflicting requirements, and it has a higher learning curve for new team members. Multi-repo challenges include the difficulty in making atomic changes across multiple repositories. Dependency management becomes more complex. Code sharing requires publishing packages or submodules. Maintaining consistent tooling across repositories is a challenge. Refactoring across project boundaries is more difficult. Duplication of configuration and infrastructure code may occur, and it needs a more complex continuous integration and continuous delivery setup across multiple repositories. When deciding between monorepo and multi-repo, consider the following factors. Team size and structure. Larger teams with clear boundaries may benefit from multi-repo, while smaller teams with shared responsibilities often work better with monorepo. Project coupling. Tightly coupled projects with frequent cross-project changes work better in monorepo. Loosely coupled projects can thrive in multi-repo. Release cycles. Independent release schedules favor multi-repo. Coordinated releases across projects are easier with monorepo. Security and access control. Fine-grained access control requirements favor multi-repo. Shared access patterns work well with monorepo. In conclusion, choose the approach based on your specific needs. Monorepo is best for teams working on tightly coupled projects with shared code, dependencies, coordinated releases, and centralized tooling and standards. Success strategies for monorepo include investing in proper tooling from the start, documenting repository structure and workflows, establishing clear ownership boundaries, and implementing automated testing and continuous integration and continuous delivery. Multi-repo is best for independent teams and projects with diverse technology stacks, fine-grained access control, and independent release cycles. Common pitfalls include choosing based on trends and not needs, underestimating tooling requirements, neglecting documentation, and failing to establish clear workflows. Consider hybrid approaches where organizations successfully implement hybrid strategies, using monorepos for related projects and multi-repos for independent systems. The best approach is often a pragmatic combination tailored to your specific needs. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this video, we will delve into using Git within integrated development environments or IDEs. I will explain how to streamline your development workflow by using Git within popular IDEs. Here are some key benefits of using Git in your IDE. It streamlines the workflow, eliminating the need to switch between the IDE and the command line for version control tasks. IDEs offer visual diff tools and intuitive interfaces for resolving merge conflicts, simplifying what can be a complex process. Operations like commit, push, and pull are integrated directly into the IDE, making them easily accessible. IDEs provide tools for visualizing and managing branches, which is crucial for parallel development. You can track the history of individual lines of code directly in the editor, aiding in debugging and understanding code changes. Let's explore the Git integration features in Visual Studio Code, or VS Code. VS Code has a dedicated source control panel where you can manage changes, commits, and branches. The inline blame feature displays commit information directly in the editor, showing who made the last change to each line. VS Code offers a visual diff tool for comparing changes between different versions of a file. Here is how to set up Git in VS Code. First, install Git if you haven't already. Then, configure Git with your username and email using the following commands. Git config, global user.name your name. Then, git config, global user.email, your .email at example.com. You can also configure VS Code settings using the settings.json file to enable smart commit and disable confirmation before synchronizing changes. Here are the settings. Git at enable smart commit, true. Git.confirm sync, false. Consider installing useful extensions like Git Lens, Git History, and Git Graph to further enhance your Git experience in VS Code. Let's look at some common Git workflows. One of the most common workflows is the feature branch workflow. First, you start from the main or master branch and create a new feature branch. Second, you develop and commit changes frequently to your feature branch. Third, regularly update your branch with changes from the main branch by pulling and rebusing. Finally, submit your changes for review and integration by creating a pull request. Here is an example in VS Code. First, create a branch using the command git checkout bfeature/login. Second, make changes and commit them using the commands git add and git commit m add login form. Here are some best practices for IDE Git integration. Use your IDE's built-in merge conflict resolution tools instead of manually editing files. Configure your .gitignore file through your IDE to avoid committing unnecessary files. Leverage your IDE's diff tools to review changes before committing them. Use your IDE's blame feature to understand code history and context. Install Git-specific extensions to enhance your IDE's capabilities. Set up keyboard shortcuts for common Git operations. And always pull before pushing to avoid unnecessary merge conflicts. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Let's explore some of the advanced features of GitHub. GitHub offers powerful tools for collaborative development. We will look at collaboration, automation, and security features to streamline your development process. Pull requests are a cornerstone of collaborative development on GitHub. Draft pull requests allow you to start a discussion and gather feedback before the code is ready for review. Linking issues to pull requests and setting up auto-closing ensures that related tasks are tracked and resolved efficiently. Required reviews and approvals enforce code quality by mandating that changes are reviewed before merging. Branch protection rules prevent accidental or malicious changes to important branches. Suggested changes let reviewers propose specific code modifications directly within the pull request. Here is an example of how to create a draft pull request via command line interface. First, check out to the feature branch. Make changes to your code. Add and commit the changes with a message. Push the changes to origin feature branch. Then create a draft pull request with GitHub command line interface, specifying the draft flag and title. GitHub Actions enables the automation of your development workflow. Upon a push event, a GitHub Actions workflow is triggered, which runs a set of jobs including build, test, and deploy, and provides automated feedback and notifications. Here is an example of a continuous integration pipeline configuration file. The name of the workflow is Continuous Integration Pipeline. The trigger for the workflow is a push to the main branch, or a pull request targeting the main branch. The job is build and test. The job runs on the latest version of Ubuntu. The steps include checking out the code and setting up Node.js. GitHub issues are essential for tracking tasks, bugs, and enhancements. Custom issue templates with form fields provide a structured way for users to submit issues, ensuring that all necessary information is collected. Automated labeling with GitHub Actions helps categorize and prioritize issues based on predefined criteria. Project boards offer a visual way to organize and track issues, making it easy to see the status of different tasks. Advanced search queries and filters allow you to quickly find specific issues based on various parameters. Issue linking and dependencies enable you to establish relationships between issues, making it easier to manage complex projects. Here's an example of a custom issue template configuration. The name of the template is Bug Report, with a description to file a bug report, a label of bug and triage, and an assignee of Octocat. The body consists of a markdown section to thank the reporter, and an input field to specify the version. GitHub projects provide a flexible way to manage and track your work visually. Projects are organized into columns representing different stages of a workflow, such as to do, in progress, in review, and done. Cards within each column represent individual tasks or issues, providing a clear overview of the project's status. The to-do column contains tasks that need to be started, such as adding user authentication and fixing a login redirect issue. The in-progress column includes tasks that are currently being worked on, such as improving search performance and adding dark mode support. The in-review column contains tasks that are awaiting review, such as updating the API documentation. The done column contains tasks that have been completed, such as fixing an image upload bug. Automation allows you to auto-assign issues and update their status as they move through the project workflow. Custom fields allow you to track priority, effort, and deadlines for each task. Insights provide burn-down charts and velocity tracking to help you monitor progress and identify potential bottlenecks. GitHub discussions provide a collaborative communication space for your community to have conversations, ask questions, and share ideas. The question and answer category is used for seeking answers from the community. The ideas category is used for sharing ideas for new features and improvements. The announcements category is used for project updates and important notices. The general category is used for open-ended conversations about the project. Here is an example discussion. The discussion is titled Best Practices for GitHub Actions. It was started by DevUser 2 days ago and is in the question and answer category. The question describes their experience with GitHub Actions and asks for advice on structuring complex workflows, managing secrets, and optimizing for speed and reliability. The discussion has 12 upvotes and 5 replies, and the question is marked as answered. GitHub Codespaces provides cloud-based development environments that can be accessed from anywhere. Codespaces offers instant setup with pre-configured environments, allowing developers to start coding without the hassle of setting up local machines. It has seamless integration with GitHub Workflow, making it easy to collaborate and contribute to projects. Customizable configuration with DevContainer. JSON enables developers to define their preferred development environment. VS Code extensions and personalization allow developers to tailor their codespaces to their specific needs. Collaboration with port forwarding and sharing enables developers to work together in real time. Here's an example of a devcontainer.json configuration file. It defines a Node.js project using the official JavaScript Node image version 18. It forwards ports 3000 and 5000. It specifies custom versus code extensions. GitHub provides several security features. Dependabot automatically detects vulnerable dependencies in your project and creates pull requests to update them. Code scanning, powered by CodeQL, automatically scans your code for security vulnerabilities and coding errors. Secret scanning automatically scans repositories for known secret formats and alerts you when credentials are committed accidentally. Branch protection enforces specific workflows, requires reviews, and prevents force pushes to critical branches. Here are some examples. Dependabot identifies a critical vulnerability in Lodash. The severity is high and the affected version is less than 4.17.21. The workflow name is CodeQL. Secret scanning detects an AWS access key. Branch protection rules for main requires pull request reviews, requires status checks to pass, and include administrators. The GitHub command line interface is GitHub's official command line tool that brings pull requests, issues, and other GitHub concepts to your terminal. It provides commands for repository management, such as creating, cloning, viewing, and forking repositories. Pull request commands include creating, checking out, reviewing, and merging pull requests. Issue commands allow you to create, list, view, and close issues. Workflow commands enable you to list, run, and view workflows, as well as list workflow runs. Here's an example of a GitHub command line interface session. First, authenticate to github.com with preferred protocol of HTTPS. Authenticate Git with GitHub credentials. How would you like to authenticate? Browser. Then, create a pull request with the title of Add User Profile Page, and the body. This pull request implements the user profile feature, creating a pull request for feature branch to main and username/repo. The link of pull request is generated. The common workflow steps are listed. Create an issue, view the issue in the web, create a pull request, check pull requests, and merge pull requests. In summary, GitHub's advanced features enhance collaboration through pull requests, discussions, and reviews, enabling seamless teamwork and code quality. Automation is facilitated by GitHub Actions, Dependabot, and command line interface tools, which streamline workflows and increase productivity. Security is reinforced with code scanning, secret detection, and branch protection, ensuring your projects remain secure. For further exploration, consider consulting the GitHub Docs, GitHub Skills, GitHub Blog, and the GitHub Community Forum. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Welcome. This video will delve into the advanced features of GitLab, focusing on continuous integration, continuous deployment, and its capabilities as a comprehensive DevOps platform. GitLab is more than just a code repository. It offers a suite of tools to streamline your entire software development lifecycle. We will be exploring CI/CD pipelines, DevOps metrics, and security features. Continuous integration and continuous delivery pipelines automate your software delivery process, allowing for faster and more reliable releases. DevOps metrics provide insights into your team's performance, helping you identify areas for improvement. Security features help you to identify and address vulnerabilities in your code early in the development process. GitLab's built-in continuous integration and continuous deployment system automates your software delivery process. The key features of GitLab CI/CD are automated testing and deployment, configuration as code with GitLab-ci.yml files, integration with containers and Kubernetes, customizable pipeline stages and jobs, and detailed pipeline visualization. As you can see here in the diagram, the pipeline stages include building, testing, security, deployment, and production. The build stage compiles the code. The test stage runs tests. The security stage performs static application security testing and dynamic application security testing. The deployment stage deploys to staging, and then the final stage is production release. The .gitlabci.yml file defines your continuous integration and continuous delivery pipeline structure, including stages, jobs, and their dependencies. Key components include stages, which define the pipeline sequence, jobs, which define what to execute, scripts, which contain the actual commands, and artifacts, which pass data between jobs. Some best practices include keeping configurations simple at first, using variables for reusable values, and validating your YAML syntax. Here is a sample YAML file. Stages are build, test, and deploy. Under the build job, the stage is build, and the script contains commands, such as echo building the application, npm install, and npm run build. Let us explore the common job types and their configurations. Some common job types include test jobs which run unit tests, integration tests, and other automated testing to validate code quality. Lint jobs which check code style, formatting, and potential errors using static code analysis tools. Deploy jobs which deploy applications to different environments like staging and production. And security jobs which run security scans like static application security testing, dynamic application security testing, dependency scanning, and container scanning. Here are some example job configurations. In a test job example, the variable unit test, the stage is test, and the script is npm run test. In a lint code example, the variable lint code, the stage is test, and the script is npm run lint. For the deploy staging job, the variable is deploy staging, the stage is deploy, the script is echo deploying to staging, and the environment name is staging. Variables are useful to make pipelines flexible and secure. There are 3 types of variables to use: predefined variables, project variables, and file variables. Predefined variables are automatically provided by GitLab with information about the pipeline and repository. Some examples include CI commit SHA, CI job ID, and CI project path. Project variables are custom variables defined in the project settings and are ideal for secrets and environment-specific values. Some examples include API token, database URL, and deployment server. File variables are defined directly in the .gitlab-ci.yml file and are best for non-sensitive configurations. Some examples include app version, build type, and environment. Here are variables defined in the .gitlab-ci.yml file. The keyword variables with the app version set to 1.0.0, and the node environment set to production. Under the build job, the stage is built and the script echoes building commit CI commit SHA, echoes app version, and echoes deploying to deployment server. Artifacts are files created during a job that can be passed to subsequent jobs or downloaded after the pipeline completes. Some common use cases for artifacts include build outputs such as compiled binaries and packages, test reports and coverage data, documentation files, and deployment packages. Some configuration options include paths, which are the files to include, expire in, which specifies how long to keep artifacts, when, which are the conditions for creating artifacts, and reports, which are special artifact types. Here is a diagram of the artifacts. The build job compiles code and passes the build directory as an artifact. The test job then tests the application and passes the test report.xml as an artifact. Finally, the deploy job deploys the app. GitLab offers integrated security scanning in your continuous integration and continuous delivery pipeline. Static Application Security Testing, or SAST, analyzes your source code for known vulnerabilities, detects structured query language injection, cross-site scripting, and more, and contains language-specific analyzers. To include it in your .gitlab-ci.yml file, include the template security/SAST gitlab-ci.yml. Dynamic Application Security Testing, or DAST, scans your running application for vulnerabilities, tests deployed applications, and finds runtime vulnerabilities. To include it in your .gitlab-ci.yml file, include the template security/DAST gitlab-ci.yml. Dependency scanning analyzes your dependencies for known vulnerabilities in third-party libraries, checks package managers such as npm and pip, and provides vulnerability reports. To include it in your .gitlab-ci.yml file, include the template security/dependency scanning gitlab-ci.yml. Container scanning scans container images for known vulnerabilities in the operating system packages, checks Docker images, and identifies operating system level vulnerabilities. To include it in your .gitlab-ci.yml file, include the template security/container scanning gitlab-ci.yml. GitLab environments are targets for deployments that represent different stages in your software delivery workflow. Key benefits include tracking deployments across environments, viewing deployment history, monitoring environment status, and manual or automatic deployments. To configure, define environments in your .gitlab.ci.yml file. As shown in the example under deploy staging, the stage is deploy, the script is /deploy.sh staging, the environment name is staging, and the URL is specified as https://staging.example.com. The deployment flow typically involves development, staging, and production environments. Development has automatic deployments for each commit. Staging has automatic deployments from the main branch, and production involves manual deployment with approval. GitLab provides metrics to measure and improve your DevOps performance. Some of these metrics include lead time, deployment frequency, change failure rate, and mean time to recovery. Lead time measures the time from code commit to production deployment, identifies bottlenecks in delivery, and helps optimize workflow efficiency. Deployment frequency measures how often you deploy code to production environments, indicates team agility, and reflects continuous integration and continuous delivery maturity. Change failure rate is the percentage of deployments that result in failures or incidents, measures code quality, and indicates testing effectiveness. Mean time to recovery is the average time to restore service after a failure, measures incident response, and reflects operational resilience. GitLab's integrated metrics help teams measure, analyze, and improve their DevOps performance over time. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. Hello and welcome. In this session, we're diving into Git for enterprise teams, focusing on how to scale Git for large organizations. Let's get started by understanding the challenges and strategies involved. Scaling Git in an enterprise environment introduces a unique set of challenges. From a technical perspective, you'll encounter issues like repository size, history management, handling binary assets and large files, continuous integration and continuous delivery pipeline integration at scale, performance with distributed teams, and resolving merge conflicts in complex code bases. Organizationally, it's about standardizing workflows across teams, managing access control and permissions, facilitating knowledge sharing and onboarding, adhering to compliance and audit requirements, and balancing team autonomy with overall governance. Gitflow offers a structured approach to manage code changes, particularly beneficial for enterprise environments. The core branch structure includes the main branch, which holds production-ready code, release branches, used for preparing release candidates, the develop branch, serving as the integration area for features, feature branches, where new functionalities are developed in isolation, and hotfix branches, for addressing critical issues in production. Gitflow promotes clear separation of concerns, allowing teams to work in parallel while maintaining stable production code. Enterprise adaptations often involve additional validation branches and automated gates between environments to ensure quality and compliance. Monorepos, which consolidate multiple projects into a single repository, require specific configurations to optimize Git's performance. To optimize Git for large repositories, set the core compression to 9, pack window memory to 256 megabytes, and pack threads to 4. Partial clones can significantly reduce initial download sizes by using the command git clone, with the filter equals blob:"none and repository link. Sparse checkouts allow developers to focus on specific directories, using the command git sparse checkout set, followed by the desired paths. Best practices for monorepos include utilizing partial clones, implementing sparse checkouts, configuring Git large file storage for binary assets, setting up branch protection rules for critical paths, establishing code owners for component ownership, and automating dependency management across projects. Git hooks enable the automation of quality gates, ensuring code meets certain standards before being committed or pushed. A pre-commit hook for code formatting might use Prettier to automatically format JavaScript, JSX, TypeScript, and TSX files. The script first checks if Prettier is installed, and if not, it exits with an error. A pre-push hook for security scanning could employ SNYK to test for vulnerabilities before code is pushed. Similar to the pre-commit hook, it verifies if SNYK is installed and exits if it's not found. These hooks are essential for maintaining code quality and security in an enterprise environment. Implementing robust branch protection and governance policies is crucial for enterprise Git management. These policies include requiring a minimum of 2 reviewers for critical branches, enforcing signed commits for all production code, implementing status checks for continuous integration and continuous delivery pipelines, restricting force pushes on protected branches, requiring a linear history for cleaner auditing, and setting up code owners for automatic reviewer assignment. A branch protection configuration file, such as .github/branchprotection.yml, can automate these policies. This file specifies rules like enforcing administrator privileges, requiring signed commits, defining required status checks such as security or SNYK, and continuous integration or Jenkins, and setting the number of required approving reviews. Managing binary assets efficiently in enterprise repositories is made easier with Git large file storage. To initialize Git large file storage in a repository, use the command git lfs install. Track specific file types like Photoshop documents, zip files, and PNG images in assets directories using git lfs track. Then, add .git attributes to the repository using git add.git attributes. The benefits of using Git large file storage include reducing repository size by storing binary files externally, improving clone and fetch performance for developers, enabling versioning of large files without bloating Git history, supporting bandwidth-efficient transfers with file pointers, and seamless integration with continuous integration and continuous delivery pipelines for asset management. Continuous integration and continuous delivery integration with Git enables robust enterprise automation strategies. These include implementing branch-based deployments to different environments, enforcing quality gates with automated testing, setting up release automation with semantic versioning, configuring auto-merging for dependency updates, establishing compliance checks for regulated industries, and creating deployment approval workflows. A GitHub Actions workflow example such as .github/workflows/enterpriseci.yml can automate these processes. This file defines when the workflow runs, such as on push or pull request, and includes jobs like validating code and running security scans using SNYK test. Measuring the effectiveness of Git workflows in an enterprise involves tracking key performance indicators. These metrics include lead time, which is the time from commit to production deployment, merge frequency, or the number of successful merges to main branches, build success rate, representing the percentage of successful continuous integration and continuous delivery pipeline runs, defect escape rate, which is issues found in production versus development, collaboration index, showing cross-team contributions and code reviews, and repository health, covering size, performance, and maintenance. Metrics. Tracking these metrics over time helps identify bottlenecks and improvement opportunities in your Git workflows. In summary, key practices for enterprise Git involve implementing standardized workflows across teams, establishing governance policies with branch protection, optimizing for large repositories with Git large file storage and sparse checkouts, automating quality gates with Git hooks and continuous integration and continuous delivery, measuring and improving Git effectiveness with key performance indicators, and investing in team training and documentation. Additional resources for further learning include materials on Git at Scale from Microsoft, GitHub Enterprise, GitLab Flow, and Dora Metrics for DevOps research and assessment. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content. In this video, we'll be exploring Git case studies through real-world examples of Git usage in major projects. By examining how different organizations and communities utilize Git, we can gain insights into effective version control strategies and workflows. Let's begin with the Linux kernel. Git was created by Linus Torvalds specifically for the Linux kernel development. It involves thousands of contributors worldwide. The Linux kernel uses a pull request workflow via email. It employs a maintainer model with subsystem branches. Here's the Linux kernel typical contribution workflow. First, use git clone to clone the repository. Then use git checkout to create a new branch for your feature. After this, make changes, then commit with git commit sm followed by a descriptive commit message. Finally, generate a patch for email submission using git format patch. Let's look at some Linux kernel Git statistics. It has more than 1 million commits, more than 15,000 contributors, the repository size is around 3 gigabytes, and it has been in use since 2005. Now let's take a look at React, which is Facebook's open-source user interface library. React uses GitHub Flow with pull requests. It uses extensive continuous integration and continuous deployment automation with GitHub Actions. It uses semantic versioning with detailed release notes. Canary releases are used for early testing. Here is the React contribution workflow. First, fork the repository on GitHub. Second, create a feature branch with a descriptive name. Third, submit a pull request with a detailed description. Fourth, pass automated tests and code reviews. Fifth, the core team merges with squash commits. The React project typical pull request workflow involves first cloning the repository. Then change the directory to React. After this, create a checkout with the name fix/component issue. After making the required changes, run yarn test. Commit the changes with a message fix. Resolve component rendering issue. Finally, push the changes to the remote repository. Now let's discuss Python. Python migrated from Mercurial to Git in 2017. It uses GitHub for contributions and issue tracking. Core developers have direct push access. Python Enhancement Proposals or PEP process is used for major changes. Protected branches with required reviews are used. Here is the migration timeline. In 2014, there were initial discussions about migration. In 2015, PEP 481 proposed Git migration. In 2016, there was test migration and workflow planning. In February 2017, the official migration to GitHub was completed. The migration challenges included converting more than 100,000 Mercurial commits to Git, preserving commit history and attribution, training core developers on the Git workflow, and updating continuous integration and continuous deployment pipelines and automation. Now let's take a look at Kubernetes. Kubernetes is Google's container orchestration platform. It is one of the largest open-source projects. It uses a special interest groups, also known as SIGs, structure. It uses a sophisticated branching strategy. It uses extensive automation with PROW continuous integration system. Here's the SIG-based contribution model. First, contributors join relevant special interest groups. Second, SIG members review pull requests in their domain. Third, approvals are required from SIG maintainers. Fourth, release teams coordinate across SIGs. The Kubernetes pull request workflow with bot commands looks like this. After making changes and pushing to fork, some common bot commands are used in pull request comments /kindbug, /signetwork, /assign@reviewer, /lgtm, /approve. Let's discuss VS Code. VS Code is Microsoft's open-source code editor. VS Code has a monthly release cycle with iteration plans. It uses feature branches with an endgame process. It uses insiders builds for early testing. It uses automated issue management with bots. Here's the VS Code release process. It involves planning, development, endgame, and release phases. Let's discuss the VS Code branch strategy. The main branch is always releasable. For feature development, create a new branch named username/featurename. For release branch creation, create a new branch named release/1.xx and create a git tag 1.xx.0. Now let's explore TensorFlow. TensorFlow is Google's machine learning framework. It has a monorepo structure with multiple projects. It has synchronized releases across components. It involves extensive use of automation and bots. It manages contributions from diverse teams. Here's the TensorFlow monorepo structure. It has a TensorFlow folder. Inside that it contains core/python/light/js/examples/tools/models/ folders. The contribution workflow highlights are as follows. Contributor License Agreement or CLA is required. Automated testing across platforms and devices is done. Special interest groups or SIGs are used for domain expertise. Synchronized versioning across all components. Nightly builds and continuous integration. Let's explore GitLab. GitLab develops on GitLab itself. GitLab has a monthly release cycle on the 22nd of each month. It has a public issue tracker and roadmap. It uses a single main branch with feature flags. It maintains transparent development metrics. GitLab uses its own platform to develop itself, providing a real-world test environment for new features. The benefits of this are as follows. Real-world testing, faster feedback cycles, better user empathy, showcase capabilities. The feature flag workflow is as follows. Develop features behind feature flags in the main branch, deploy to production with features disabled, enable features gradually for testing groups, roll out to all users when stable, and remove feature flag code in a future release. Here are the key takeaways from these Git case studies. Git adapts to different project needs, from email-based patches to pull requests to feature flags. Projects like Kubernetes and TensorFlow demonstrate Git's ability to handle massive codebases with thousands of contributors. All major projects leverage automation with Git hooks, continuous integration and continuous deployment pipelines, and bots to maintain quality and velocity. Different projects implement various governance structures while using the same Git tools. Public repositories, commit histories, and issue trackers create accountability and enable community participation. Code review processes, automated testing, and branch protection rules ensure high-quality contributions across projects. Git's flexibility allows each project to develop unique workflows that match their specific needs, team structure, and release cadence, while maintaining the core benefits of distributed version control. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.